The cosmic mystery of an October rendezvous in 2022 marked the first time in recorded history for a strange phenomenon, as two distinct cosmic objects simultaneously journeyed toward the Sun, from completely different origins. The interstellar wanderer was confirmed to carry chemical signatures that defied every rule of star formation known to science. Meanwhile, Swan Rice brightened at an astonishing rate, revealing a composition completely unlike anything from our solar system's Oort cloud. This combination created a celestial traffic jam, a phenomenon that, mathematically, should only occur once every few million years. But now, both were approaching the Sun just 28 days apart. Ground control centers were tracking the converging trajectories with absolute precision, as instruments detected chemical anomalies that were challenging decades of cometary research. But this is where the story becomes intriguing. As both objects descended deep into the Sun's glare, telescopes would be completely obscured from view during the most critical phases. What if this timing was not accidental? What if there was something that did not want us watching? Let's explore why October of 2022 could rewrite everything we thought we knew about what is truly happening out there. Part 1. Two lights in the sky. The arrival of mysterious visitors. Two strange objects that had come to our solar system, carrying mysteries from the deep reaches of the cosmos. One of them, slender and swift, bearing a strange blue light, as if illuminated by an energy source, not of this world. The other was vast and brilliant, with its tail stretching for degrees across the sky like a vast cosmic canvas painted with light. They came from different corners of the vast universe, from regions of space, from which light must travel for millions of years to reach Earth. But now, in a strange cosmic arrangement, they were converging on our Sun, in a beautiful and mysterious cosmic dance, causing astronomers all over the world to check and recheck their complex calculations. The first visitor, Atlas. This visitor first appeared on a sunny day, on the 1st of July, 2022, through the sophisticated digital eye of the Survey telescope. Atlas in Chile. It was just a single pixel of light, faint and seemingly harmless, a point of light that should not have been there. According to all existing astronomical models, just a few hours after its discovery, complex orbital mechanics calculations revealed an astonishing truth. This object was officially designated by scientists as Bi-Atlas. It was moving on a strange hyperbolic orbit, an orbit unbound by the gravitational pull of our Sun. This was a true interstellar wanderer, the third visitor, confirmed to have come from beyond the distant edges of the solar system. The second visitor, Comet Swan. The second visitor appeared just a few months later, like a phantom emerging from the Sun's glare. Comet C. 2.00215. GI, or as astronomers call it, Swan, appeared at dawn during a routine survey. It was discovered in photographs of the constellation Cygnus on September 11th, 2012, and from the very first observation, it was bright enough to be seen with ordinary binoculars. Notably, from the moment of its discovery, Swan already had a brilliant tail, a phenomenon that amateur astronomers around the world described as stunning and unbelievable. That tail was like a giant brushstroke painted across the black canvas of the night sky. In the halls of science, in the sterile and silent corridors of NASA's Jet Propulsion Laboratory, powerful supercomputers hummed, with the constant whisper of data streaming in from around the globe. Giant radio dishes across the planet were tracking these mysterious visitors, with mechanical precision, as steady as the heartbeat of a perfect machine. Each data packet that arrived told its own unique story. Bright curves displayed on screens, complex spectral signatures, precise orbital measurements calculated down to the 10th of an astronomical unit. But the numbers, no matter how precise, could not fully capture the beauty and mystery hanging in the night sky above us. The spectacle in the night sky. Try standing outside on an October evening, clear, far from the glaring orange lights of the city, and you might catch a glimpse of both these strange visitors. By Atlas appearing as a faint smudge through a telescope, a modest one, but its characteristic green hue was subtle yet unmistakable for keen and experienced eyes. Meanwhile, Comet Swanry dominated the western horizon just after sunset, with its magnificent tail sweeping up like a giant cosmic brushstroke, painting the darkening sky with indescribably magical streaks of light. The language of machines, of scientific instruments, spoke in frequencies the human ear could not hear. The dense ticking of a CCD shutter recording every photon of light that had to travel for millions of light years to reach us. The electronic whisper of the spectrometer, meticulously separating the light from the stars into its basic constituent elements. Ground-based observatories around the world were constantly relaying their scientific findings into data streams that flowed like digital rivers toward analysis centers where the most brilliant minds of humanity were trying to interpret what their sophisticated machines were seeing. But space itself remained forever silent, with no sound able to travel through the vast vacuum between worlds. Only electromagnetic radiation bridged the enormous distances, carrying information intricately encoded in the wavelengths of light, telling us that these objects were not entirely what we thought they were. The true nature of Bi-Atlas. Bi-Atlas moved with the deliberate speed of something that seemed to know exactly where it was going, according to a pre-established plan. Its carefully calculated orbit set it on a path that would bring it closest to our Sun on the 29th of October, 2002, at a distance from the central star of our solar system of exactly 1.35 astronomical units. This was a distance just inside the orbit of Mars, and for a visitor from interstellar space, this represented an extremely close approach, close enough that some cautious scientists began to ask uncomfortable and worrying questions. The schedule of Swanry. Comet Swanry followed its own schedule with astonishing precision. It reached perihelion, its closest point to the Sun, on the 12th of September, 2002, dipping to within half an astronomical unit of the star's blazing surface, before beginning its long journey out of the solar system. But its closest approach to Earth will follow later on October 21st, when it will pass within just 0.17 astronomical units from our homeworld, in cosmic terms, and by the standards of astronomical measurement. This is practically grazing the edge of our atmosphere, a disquieting moment. It is this strange coincidence that is causing astronomers around the world to lose sleep, staring at their computer screens long after their colleagues have gone home to rest. Two objects from entirely different origins are converging on our inner solar system within a matter of weeks. Complex probability calculations suggest that this should be incredibly rare, an event that might only occur once in millions of years. Yet, here we are, witnessing what could be the most incredible coincidence in all of astronomical history, ever officially recorded. Or perhaps, and this is the more frightening thought, this is not a coincidence at all. The chemical mysteries, the characteristic green hue of Comet Atlas, have drawn particular attention from the international scientific community. Detailed spectral analysis reveals the distinct presence of carbon molecules and diatomic cyanogen, which emit a characteristic green fluorescence when excited by the intense radiation from the Sun. In theory, this is perfectly natural for a conventional comet, beginning its outgassing process as it approaches our star. But the unusual intensity and suspicious consistency of this color have surprised, experienced researchers who have dedicated their long scientific careers to studying these mysterious wandering celestial bodies. Comet Swan also holds its own chemical mysteries, which are no less intriguing. Its suspiciously rapid brightening, as it emerged from its close conjunction with the Sun, suggests a chemical composition entirely unlike that of typical comets from our solar system's familiar Oort cloud. The development of its tail follows familiar physical laws, but there is something subtly different about it, as if it is following a script, written in a language slightly alien to anything we have known before. The contrast in size. Size is a critically important factor in outer space, and so is the contrast between our two visitors. It could hardly be more dramatic and contrasting. Comet Atlas appears as a compact and purposeful needle of light. Current estimates based on its brightness suggest a nucleus perhaps only a few kilometers in diameter. Modest by typical cometary standards, yet still large enough to generate the luminous activity that we can observe from Earth. In stark contrast, Comet Swan spreads across the sky like a vast veil of light, with its coma and magnificent tail stretching for degrees as seen from Earth, creating a truly spectacular sight. As the late October approach nears, we are day by day drawing closer to two cosmic visitors that are relentlessly hurtling toward their closest approaches to our blue planet. Interestingly, Mars will have a particularly favorable position to witness Comet Atlas on the 3rd of October, when the red planet's orbit brings it to within just 30 million kilometers of the interstellar wanderer. The faithful robotic emissaries that we have sent to orbit Mars, the sophisticated cameras and spectrometers that we have carefully placed there, will turn all their observational instruments toward this approaching visitor, gathering precious data that might finally answer some of the questions that have been mounting with each new observation. The challenge of sunlight. But there is a serious problem with October as both objects approach their closest point to the Sun on their journey. The view from Earth will become increasingly difficult and limited, as the glaring light of the Sun will eventually swallow both visitors in its glare, blinding our ground-based telescopes completely during the most crucial phases of their scientific journey. For many weeks, perhaps for long months, we will completely lose track of them, and only when they re-emerge from behind our star, if they re-emerge at all, will our scientific instruments be able to continue the story. The haunting questions remain: will they be unchanged, bearing only the scars expected from their close encounter with the Sun, or will they carry evidence of something more profound? Something that completely challenges our understanding of what moves among the stars in the vast cosmos. This question haunts the cold October nights. It sounds simple, yet is unbelievably complex. Are they comets or a fortress from a distant civilization? Or perhaps they are the response to a message we never knew we had sent. The universe has placed two great mysteries in our skies. In the year 12,012 may lie our only chance to decipher them, before they disappear forever into the endless darkness of the universe. But first, we need to understand clearly how we found them, and more importantly, how did they find us? Part 2. The Whispering Devices. The discovery begins with patience. The discovery of these mysterious cosmic visitors did not begin with a dramatic moment of sudden revelation, but with the patient accumulation of millions of photons of light upon the sensors of silicon scattered across our blue planet. Each night, as darkness blankets half the Earth, automated telescopes begin their work of scanning regions of the sky, predetermined with absolute precision. Their ultra-sensitive electronic eyes ceaselessly capture images that will be compared, processed, and scrutinized by complex, specially designed algorithms to recognize what should not be their strange points of light, unusual movements, the signs of the presence of something from beyond the solar system. The Global Observation Network, the Atlas System, the First Sentinel. The Atlas survey operates through a network of 4 modern telescopes spread across 26 locations. Each telescope is equipped with advanced cameras capable of monitoring vast swaths of the sky. And on each clear night, they generate hundreds of gigabytes of immense data, recording millions of stellar positions measured with phenomenal precision. Detecting an interstellar visitor from this massive flood of information is like finding an anomalous point of light moving too quickly and in the wrong direction, compared to all the surrounding stars, a task that requires the perfect combination of technology and artificial intelligence, a global chorus. But Atlas is just one voice in the global chorus of automated sentinels. The Catalina Sky Survey in Arizona, Linear in New Mexico, and NeoWise floating above Earth's atmosphere, all contributing to a network of eyes that never sleep, never blink, never miss any change in the cosmic order. The combination of professional and amateur discovered Comet Swan when it appeared in data from the observatory of the Sun and heliosphere. Interestingly, it wasn't NASA's professional astronomers who first spotted it. Instead, amateur astronomer Vladimir Bezugli, while reviewing images from the Swan system for his own personal research, noticed an unusual brightening that would later become one of the most spectacular comets of 2012. This is the nature of modern astronomy, how it operates in the digital age. Professional and amateur observers, silicon sensors and human intuition, all working together to capture the fleeting moments when something new enters our cosmic neighborhood. The instruments whisper their secrets in the dry language of counts, of photons and pixel intensities, but it takes profound human insight to recognize when those whispers are trying to tell us something important. The language of light. Different specialized instruments reveal different truths about our celestial visitors. Visible light cameras show us the overall structure, the bright nucleus, the expanding coma, and the tail sweeping away from the sun, like a giant cosmic weather vane. But to understand what these objects truly are, we need to break their light down into its fundamental constituent colors. Spectroscopy is the key that turns celestial light into valuable information, a chemical fingerprint. As molecules in the comet's thin atmosphere absorb and re-emit the powerful radiation from the sun, they create characteristic chemical fingerprints in the light spectrum that we receive. Observations of Atlas using the Very Large Telescope have revealed surprising and intriguing details. The data showed strong emission lines from cyanogen, and even more surprisingly, from nickel atoms, glowing in the cold vacuum of space. The presence of nickel is not unprecedented in comets, but it was unusual enough to warrant attention from the international scientific community. The puzzling chemical mysteries, the strange absence of iron. What was more interesting and puzzling was that the Very Large Telescope, VLT, did not detect the iron emission lines that usually accompany nickels in natural samples on Earth. This unusual absence of iron, combined with the signature of strong nickel, created a chemical fingerprint that did not quite match expectations based on our current understanding of how comets form and evolve in the universe. Discoveries from the James Webb Space Telescope, with its ultra-sensitive infrared eyes, was pointed towards Atlas in August of 2022 and revealed a composition of primarily carbon dioxide with relatively little water vapor, at least at the great distance where these observations were made. This is consistent with a comet having an outer layer rich in volatile ices that sublimate at lower temperatures, creating activity long before water ice began to contribute significantly to the observed comet's coma. Advanced observation technology. The Swan system. Images from the Swan system provided a completely different perspective. The Solar and Heliospheric Observatory, through its Swan instrument, can map the distribution of hydrogen atoms created when water molecules are broken apart by the sun's intense ultraviolet radiation. This gives us a full three-dimensional view of how water vapor spreads through the space surrounding active comets. revealing subtle details that are invisible to conventional telescopes. The Hubble Space Telescope contributed stunning high-resolution images, helping to constrain the size of Atlas's nucleus to just a few kilometers, large enough to produce observable activity, but small enough to have escaped detection until it was deep within our solar system. The challenge of technology is that our instruments can be misleading. Each observation adds another piece to the overall picture, but that picture grows increasingly complex with each new data set. However, advanced tools can deceive as well as reveal the truth. Automated processing and telescopic image analysis systems are designed to identify known patterns, the predictable behavior of objects in Keplerian orbits around the Sun. When something behaves differently, even just slightly, those differences can be masked by the very algorithms designed to efficiently classify the data. The measurement challenge. Consider the complex challenge of measuring changes in brightness. Comets do not brighten uniformly as they approach the Sun. Instead, they undergo complex transformations due to the sublimation of different types of ices at various distances, the rotation of irregularly shaped nuclei, and the release of dust and gas in bursts from active regions. Distinguishing between natural variation and truly anomalous behavior requires careful analysis by experts who understand the subtle nuances of cometary physics. The mystery of green 6. The green 6 color observed on Comet Atlas clearly illustrates the complexity of analyzing how certain molecules can produce the green 6 emission under the conditions found in a comet's coma. Diatomic carbon is the most common cause of the green 6 glow when excited by solar radiation. Cyanogen can also contribute to this green 6 color. Without a high-resolution spectrometer to precisely identify the responsible molecules, the green 6 hue remains merely suggestive, not a definitive diagnosis. The challenge of science communication. The media, when reporting on unusual astronomical discoveries, often tends to amplify the uncertainty into sensationalism. When preliminary reports mention unexpected chemical signatures or unusual orbital characteristics, those details can be turned into evidence for extraordinary interpretations long before the peer review process has a chance to confirm or refute the initial observations. The scientific process is designed to be self-correcting, but that correction often happens more slowly than the public's demand for quick and definitive answers. An anchor to reality. This is where the instruments become most important, not just as detectors of cosmic phenomena, but as anchors to reality amidst a sea of speculation and hypotheses. Telescopes are indifferent to human desires for dramatic discoveries. They simply and faithfully record photons and measure positions, building an objective database of observations, which will ultimately reveal the truth. Regarding safety, observations add another layer to this analysis. Both Atlas and Swan are on orbits that keep them safely distant from the Earth. Comet Atlas will come no closer than 1.8 astronomical units, which is about 270 million kilometers. Comet Swan will make its closest approach at 0.27 astronomical units, still over 40 million kilometers away. This is not a threat to our planet, but a precious opportunity to study objects that formed under very different conditions than those in our familiar solar system. The challenge of time. The greatest challenge now is time. As the moment of passage draws near, both visitors will sink deeper into the Sun's brilliant glare. As viewed from Earth, ground-based telescopes will lose the ability to track them during the most fascinating phase of their solar encounter. Space-based observatories perform better in these conditions, but they have limited observation time and must balance these targets against other pending scientific priorities. In conclusion, what emerges from this sophisticated chorus of instruments is a picture painted with data points, spectral lines, orbital elements, and light curves, but such pictures can be interpreted in many different ways. And the crucial question remains, what will happen? If the ones being deceived are the instruments themselves, or the expectations of those who interpret them. The telescopes will continue their vigil, patiently accumulating photons and measuring positions with unwavering mechanical precision. But as our visitors descend toward the sun, the whispers from the equipment will grow fainter, leaving us to wonder what secrets might lie hidden in the growing quiet that lies ahead. Part 3. The language of metals, the vocabulary of atoms. Deep space speaks to us in the rich vocabulary of atoms, and Comet Atlas is telling us a story written in a completely unexpected and mysterious dialect, as the Very Large Telescope, or VLT, turned its incredibly powerful spectrograph toward this strange interstellar visitor. It had discovered something that caused astronomers around the world to stop and completely recalculate their initial predictions. Nickel vapor was glowing brilliantly in the cold vacuum near the comet's nucleus, but it was not accompanied by the emission of iron that should have been there. According to all known laws of cosmic chemistry, in the complex field of spectroscopy, every element leaves its unique signature in light when its atoms are excited by powerful radiation. From the sun or through collisions in space, they emit photons at very specific wavelengths, fingerprints as unique and recognizable as human DNA, unmistakable and impossible to fake. Nickel atoms produce characteristic emission lines in the green part of the spectrum, contributing to the ethereal color that made Comet Atlas a favorite target for astrophotographers around the world. But according to all existing scientific knowledge, nickel rarely travels alone in the vast universe. In meteorites, asteroids, and the few comets where nickel has been detected, it usually appears alongside iron in a strict ratio, reflecting the nuclear processes that created these elements in the fiery cores of stars. Billions of years ago, models of elemental abundance in the universe, carefully documented in the periodic table, show that wherever you find nickel, iron should appear in a precisely predictable ratio. But Comet Atlas seemed to have missed that particular basic chemistry lecture. The observations from the VLT were made as the comet approached its peak brightness in August 2012 and revealed strong nickel emission lines, standing out clearly against the background. However, the same observations searched for the signature of iron and found almost nothing of significance. The upper limit of detected iron was astonishingly low. If iron had been present in its normal cosmic abundance, it would have been easily detectable with modern instruments. This unusual chemical signature has generated many theoretical explanations from the international scientific community, with each one attempting to reconcile the strange observations with long-established physics. Perhaps nickel-containing organic compounds are stable in the cold of interstellar space, and are preferentially broken down by the intense heat of the sun to release nickel atoms. Or perhaps space weathering processes over millions of years have altered the surface and chemical composition of this wandering iceberg in ways we do not yet fully understand. After all, the universe is under no obligation to conform to human expectations of how elements should behave according to terrestrial logic. For historical context, Comet Borisov, the previously discovered interstellar visitor, exhibited its own chemical peculiarities when analyzed by the world's most powerful telescopes. Its ratio of carbon monoxide to water was significantly different from comets born in our solar system, suggesting formation in a colder and more carbon monoxide-rich environment around its distant parent star. But by Atlas pushes these chemical anomalies into even more fascinating and mysterious territory. Discoveries from the James Webb. Detailed infrared observations from the James Webb Space Telescope reveal a composition dominated by carbon dioxide, with water vapor playing a surprisingly minor role at the large distances where these measurements were taken. This pattern, with carbon dioxide leading the vaporization parade, followed by water as the comet draws closer to the sun, suggests an onion-like layered structure, with the most volatile ices on the outermost layer, cyanogen. the molecule likely responsible for much of the characteristic green glow, adds another layer to this complex chemical portrait, with its CN emission lines appearing prominently in the spectrum, consistent with organic compounds being broken down by the intense ultraviolet radiation from the sun. However, the finer details, the relative intensities of the various emission features, do not perfectly match the patterns seen in typical solar system comets, suggesting subtle differences in composition or structure that we do not yet fully grasp. The captivating green color has captured widespread public attention, but it also carries its own scientific mysteries. While diatomic carbon is often cited as the primary source of the green color in comets, the specific molecules responsible for the characteristic green glow of Atlas have not yet been definitively identified. Cyanogen could contribute to the green emission, much like some excited states of carbon molecules, but without a spectrum of extremely high resolution. The exact culprit remains unidentified. The green hue remains alluringly vague and mysterious, a chemical story. These chemical signatures combine into a story that challenges simple classification. If atoms are letters and molecules are words, then Comet Atlas is writing in a dialect that is primarily carbon dioxide with a slight metallic accent, not quite following the familiar grammar of Earth. It is a chemical symphony that makes sense in the context of comet formation around other stars, but unusual enough to merit the special attention it is receiving. The rate of gas production, the rates at which different gases are produced, provides another important clue about the true nature of this visitor. As Comet Atlas approaches the Sun, the rate at which it produces different molecules increases predictably as the distance decreases. This follows the expected laws of physics. For sublimating ice, where the closer to the Sun, the more rapidly frozen volatiles transition directly from a solid to a gaseous state. The mathematics of this process are well understood, allowing scientists to predict future activity levels based on current observations. However, within this predictable framework, small anomalies persist. In these persistent anomalies, the ratios between different types of molecules do not quite match the models based on comets in our solar system. The light curve shows variations, suggesting compositional inhomogeneities on the surface of the nucleus, or perhaps discrete outgassing events triggered by subsurface processes that we can only speculate about. The contribution of the amateur community. The amateur astronomy community has contributed significantly in documenting these chemical mysteries. High-quality images from backyard observers around the world have documented the evolution of the comet's structure and tail morphology as Comet Atlas continued its approach to perihelion. These observations provide a temporal range and coverage that professional telescopes, with their limited observing time and competing research priorities, simply cannot match. On social media, certain aspects of these chemical anomalies have been amplified, sometimes transforming preliminary scientific findings into sensational headlines that go far beyond the actual data. For example, the observation of nickel without iron was hastily interpreted by some as evidence of an artificial structure, with engineered metallic components, rather than natural accretion. This interpretation requires extraordinary leaps of logic, going far beyond what the spectral data actually supports. Scientifically, the official stance, NASA's position, remains clear and consistent. Current observations are entirely consistent with a natural phenomenon, a cometary visitor with unusual chemical characteristics, but not unprecedented in the history of cosmic observation. The agency's scientists emphasize that chemical peculiarities are entirely to be expected for objects formed around other stars, where temperature, pressure, and the abundance of different elements can create a different composition, entirely from anything in our familiar solar system. The perspective of the European Space Agency, or ESA, through its various missions and ground-based observation campaigns has reached similar conclusions. While acknowledging the unusual aspects in the spectrum of Atlas, ESA researchers note that the fundamental physics of cometary activity, where sublimating ice creates the observed gas and dust, provides a coherent framework for understanding these observations, without needing to invoke exotic or supernatural explanations. Regarding future research, science progresses through the careful examination of anomalies, and Atlas presents enough chemical oddities to keep researchers busy for years to come. The nickel emissions, the dominance of carbon dioxide, the cyanogen signatures, the mysterious green color. Each observation adds a piece to a complex puzzle that may ultimately teach us a great deal about the distant star system, where it was born, as well as about this special visitor itself. The challenge of time. As 2022 passed, and Atlas sank into conjunction with the Sun, the opportunities for continued detailed spectral analysis were worryingly diminishing. The combination of increasing distance from Earth and decreasing solar elongation would eventually make observations from ground-based observation becomes impossible, at least until the comet emerges from behind the Sun a few months later, if it does indeed reappear. Epilogue: the mysterious language. If chemistry is a language, then we are reading a strange dialect of ice and metal, speaking of the conditions of its formation, perhaps hundreds of light years away in a distant star system. Does that syntax follow the grammar of physics and chemistry as we understand it, or hint at something more deliberately structured? That remains the central mystery of the October sky, of our wonder. Atoms never lie. They cannot. But they do not necessarily tell us everything we wish to know about the deep secrets that they carry from the dark reaches of the cosmos. Part 4. Two paths, one dance, the cosmic clockwork. Imagine the solar system as a vast, intricate, and perfect clockwork mechanism, with the planets tracing out precisely predictable ellipses round our central star, while smaller bodies like asteroids, comets, and the occasional mysterious interstellar wanderer follow paths that intersect and diverge, according to the strict mathematical laws of gravitational mechanics. Now imagine two visitors, arriving from completely different directions, on completely different trajectories, yet aligning their closest approach to our Sun, to within just a few weeks of each other. The probability of such a coincidence should be infinitesimally small, bordering on the impossible. Yet here we are in October 2022, witnessing this exact enigmatic scenario unfolding right above our heads. The journey of Bi-Atlas. Bi-Atlas emerged from the direction of the constellation Coda of Ophiuchus in early July, its discovery marking the moment when this latter visitor became bright enough for our automated sky surveys to detect and calculate its trajectory. The data revealed it was traveling on a hyperbolic trajectory, the undeniable mathematical signature of an object not gravitationally bound to our Sun. With an orbital inclination of about 175 degrees, it was moving retrograde relative to the planets, entering the solar system from beneath the ecliptic plane, like a cosmic salmon swimming upstream, contrary to the natural flow of the planet's motion. The story of Swanray. Swanray tells a completely different tale. This object being a long-period comet, visitors from our distant Oort cloud, where they spend most of their existence, in the frigid regions at the edge of the solar system, before gravitational forces from distant disturbances push them into the inner regions, where the Sun's heat brings them to brilliant life. It appeared near the constellation Virgo, emerging from the bright glare of the Sun that had hidden it from our view during its initial approach. The geometry of these discoveries reveals important clues about the nature of both mysterious observation-defying objects. Atlas remained hidden until it was deep within our solar system, because interstellar visitors approaching from random directions often spend months or years in regions of the sky too close to the Sun to be observed effectively. By the time Atlas was found, This cosmic wanderer had already crossed Jupiter's orbit and was beginning to show the first signs of cometary activity. Swan ray, however, faced a different observational hurdle, known as the long-period comet Holocheck effect. They often brighten dramatically as they approach the sun, but this brightening occurs while they are still at a small distance from our star. Viewed from Earth, they remain hidden in the sun's glare until their orbits carry them away from the solar horizon and appear in the twilight sky. That is precisely what happened with Swan Ray in September of 2002-12, the suspicious cosmic schedule. The convergence of their key milestones creates a cosmic timeline that reads as if someone had carefully planned it in advance. Swan Ray reached perihelion on September 12th, diving to just 0.5 astronomical units from the Sun. Atlas would make its closest approach to Mars on October 3rd, passing within 30 million kilometers of the red planet. Atlas reached its perihelion around October 29th or 30th, approaching within 1.35 astronomical units of our star. Swan Ray made its closest approach to Earth around October 21st, when it passed within 0.27 astronomical units of our world. Statistics and probability. The concentration of these significant events within a 6-week period has surpassed the bounds of ordinary coincidence. If these were evenly distributed random events over time, the probability of such a close temporal correlation would be extremely low, almost impossible. However, statistical mechanics also teaches us that extremely improbable events become almost inevitable. With enough time and enough opportunities, in a universe containing billions of comets and the occasional interstellar visitor, perhaps we are simply witnessing one of those rare moments when the cosmic dice roll in a completely unexpected way. The contrast in scale, the contrast between our visitors, beyond their origins and orbits. Comet Atlas appears as a compact needle of light, with its activity confined to a relatively small region around its nucleus. Current estimates suggest a nucleus perhaps only a few kilometers in diameter, large enough to produce the observed coma and tail, but modest compared to the largest comets in the solar system. In contrast, Comet Swan presents itself as a cosmic spectacle of entirely different proportions. Its coma stretches for degrees across the sky when viewed through binoculars, and its tail has been reported to be up to 2 degrees long by experienced observers. This represents a physical scale measured in millions of kilometers, a structure so tenuous and fragile that its density rivals a laboratory vacuum, yet is visible across interplanetary distances due to the sheer volume it occupies. The beauty and challenge of autumn. The poetic beauty of this convergence unfolds against the backdrop of Earth's changing seasons. As autumn progresses in the northern hemisphere, both celestial bodies sink lower toward the western horizon after sunset. Comet Swan dominates this astronomical stage, easily visible to anyone with a good pair of binoculars and a clear view toward the constellation Virgo. Comet Atlas requires more serious equipment to observe, but its characteristic green hue makes it unmistakable. Once its precise location is identified, the October Observing Challenge. Yet, October brings both challenges and opportunities. The same geometries that create the close approaches to the Sun also simultaneously, making detailed observations increasingly difficult as both objects approach their perihelion. They sink deeper into the Sun's glare as seen from the Earth. Eventually, ground-based telescopes will lose the ability to track them. During the most scientifically interesting phases of the journey, this period of non-observation is not just an inconvenience, but a gap in our knowledge that could prove to be crucial to understanding what these visitors truly represent during the weeks when Earth-based telescopes cannot observe them. Both objects will experience their most intense heating from the Sun, should anything unusual happen. If any hidden features are to be revealed, it will likely happen during these invisible weeks. The complexity of retrograde motion, The retrograde motion of Bi-Atlas adds another layer of complexity to its orbital mechanics. Retrograde objects, compared to the planets, experience different patterns of gravitational perturbations that can potentially affect their long-term trajectories in subtle yet measurable ways. These effects can be used to constrain the mass and internal structure of the strange object, as long as we can track it accurately enough before and after its solar approach. Mars, the frontline observatory. Mars serves as our frontline observatory. During Bi-Atlas's closest approach on October 3rd, the fleet of spacecraft orbiting Mars, missions originally designed to study Martian weather and geology, will turn their instruments toward this passing visitor. These observations will be opportunistic, rather than pre-planned, but they might provide the only clear view we have of Bi-Atlas. During its critical solar approach phase, observation plans from the ESA, the European Space Agency, has announced plans for Mars-based observations, using the ExoMars Trace Gas Orbiter and other assets in orbit around the Red Planet. These spacecraft carry spectrometers and imaging systems capable of resolving details that are invisible to Earth-based telescopes. The vantage point from Mars will be particularly favorable during the flyby, providing a view of the comet's coma and structure, and the development of its tail, complementing our observations from Earth. Unanswered questions. Despite multiple perspectives and the most sophisticated instruments, fundamental questions still lack satisfactory answers. The coincidence in timing continues to puzzle researchers, who have dedicated their entire scientific careers to studying the statistical mechanics of solar system dynamics, in a universe where encounters, by chance, often span millions of years. Why would we witness two distinct visitors so significantly arrive at nearly the same time? The conclusion, poetry or plan. If these two cosmic paths form a rhythmic dance, is it the poetry of nature or an intentional plan? This question not only challenges our scientific understanding of cosmic mechanics, but also forces us to consider possibilities that we may not yet be ready to accept. As the two visitors continued their journey through October of 2012, they carried with them not only chemical and physical mysteries, but also a deeper question about the nature of coincidence in a universe that seems to be governed by precise and predictable laws. Part 5. Theories arranged like constellations. Pattern-seeking machines. Human brains are sophisticated, pattern-seeking machines, evolved over millions of years to find meaning in chaos and purpose in randomness. When faced with two cosmic visitors, arriving at our sun within a few weeks, exhibiting unusual chemical characteristics, and following trajectories that seem intentionally orchestrated, those minds begin to construct narratives that go far beyond what the data actually supports. These narratives range from the merely strange to the truly extraordinary, each offering a different lens through which to view the mysterious convergence of October 2012, the Scout and Fortress hypothesis, the reconnaissance mission. One of the most audacious theories posits Atlas as an advanced, agile, and maneuverable reconnaissance probe, tasked with surveying the resources of our solar system, as well as potential defense systems. Swan Dry, in this scenario, serves as the main base, a mobile outpost or communications relay station capable of supporting extended operations within the inner solar system. The timing of their arrival is not random, but carefully coordinated, representing phases of a larger mission, beginning many years or even many decades ago in the cold of space, among the stars. A maintenance operation. Another interpretation of this activity suggests that both objects are part of an ancient infrastructure. Automated systems follow predictable cycles to maintain equipment or update programs scattered throughout our galactic neighborhood. Bi-Atlas could be carrying software updates or replacement parts, while Swan Rai provides the manufacturing capabilities or the necessary power source for major system overhauls. In this view, our solar system is merely a stop on the route of a routine service for a vast technological network, the ancient patrol concept, a surveillance network. Imagine these visitors as remnants of a surveillance network established millions of years ago by a civilization concerned with the potential development of dangerous intelligence in their cosmic neighborhood. When our radio signals began to leak out into space over the last century, dormant systems may have been activated. They deployed both reconnaissance elements and larger platforms to assess the threat level that humanity's emerging technology might represent to the existing cosmic order, a response to an unintentional message. Perhaps most compellingly, some suggest that these objects are a response to humanity's unintentional message sent to the stars. Our radio and television broadcasts, our radar systems, and satellite communications have been expanding outward at the speed of light for many decades, creating an ever-growing bubble of electromagnetic signatures around our planet. If someone or something has been listening, then by Atlas and Swan Rai could be their reply, appearing not by chance, but as a direct response to our coming of age, technologically. The techno-artifact hypothesis. The techno-artifact hypothesis proposes an even stranger possibility, that they might be artifacts of human civilization itself, launched in some future era when our descendants achieve interstellar travel, and then sent back in time or along a designed trajectory to appear at specific moments in our past. Chemical composition and unusual orbital characteristics could reflect fabrication engineering or materials science, far beyond our current understanding, but still recognizably of human origin, from a distant future. Mythological interpretations, omens in the sky, mythological interpretations that draw parallels with ancient stories of comets, omens in the sky, and unusual astronomical phenomena that have heralded major historical shifts. Every culture on Earth has legends about lights in the sky, signaling the rise and fall of kingdoms, the arrival of prophets, or the end of the world. Perhaps Atlas and Swan Ray represent a modern expression of these archetypal patterns. Cosmic punctuation marks separating one era of human development from the next, the predator and protector dynamic. A more ominous perspective offers a predator and protector dynamic. If Atlas represents a threat, a weapon system, or an invasive probe, then Swan Ray could be a defensive response or deploy by the same civilization as a safeguard against their own technology, or sent by another intelligence to neutralize the danger before it reaches us. The convergence in October 2012 becomes a celestial battlefield, with Earth as the unwitting prize. The limitations of conventional astronomy, scientific blind spots. These speculative frameworks gain traction in part because they address a fundamental limitation of astronomy, conventional astronomy, the assumption that anomalous phenomena must have natural explanations. This assumption has served science very well, driving discoveries from stellar evolution to black hole physics to exoplanets, but it also creates blind spots, areas where strange possibilities are dismissed not because evidence contradicts them, but because they fall outside the accepted theoretical framework. The perspective of Avi Loeb, the Harvard astronomer who gained worldwide attention for his proposals about the object Oumuamua being potentially artificial, has extended similar arguments to Atlas, pointing to its anomalous chemical signatures, the precise timing of its approach to the sun, and its apparent coordination with sunrise, as potential signs of technology rather than natural origins. His arguments emphasize that extraordinary claims require extraordinary evidence, but also that when extraordinary evidence appears, it deserves extraordinary consideration. The official stance NASA and the ESA, NASA and the European Space Agency maintain more cautious positions, stressing that current observations remain consistent with natural explanations, despite their unusual characteristics. Agency scientists note that our sample of interstellar visitors remains extremely small, with only 3 confirmed objects in the past 6 years, making it difficult to establish what should be considered normal or anomalous for this population. Methodological questions. The tension between these viewpoints reflects deeper questions about scientific methodology and the nature of evidence. How anomalous must an observation be before we seriously consider explanations that challenge our fundamental assumptions about the universe? How do we balance scientific conservatism with the risk of missing truly revolutionary discoveries? The role of the media. Amplification and distortion. The media has amplified certain aspects of these debates while downplaying others. Unconfirmed observations of Nican received sensational coverage on social media platforms, often accompanied by speculation about industrial processes or manufacturing marks that go far beyond what the spectral data actually supports. Meanwhile, the genuine scientific puzzles posed by Atlas, its unusual volatile composition, the precise orbital timing, the coordination with sunrise have received less attention, despite being more firmly grounded in observational data. The psychology of conspiracy thinking. The tendency to see intent. The psychology of conspiracy thinking also plays a significant role in how these theories develop and spread. Humans have a natural tendency to see agency and intent in random events, especially when those events seem to have significant implications for our future. The idea that cosmic visitors might be intentionally sent, rather than chanced upon, satisfies deep psychological needs, profound questions about meaning and control in a seemingly chaotic and meaningless universe. Historical precedents, caution, and encouragement. Historical precedents offer both caution and encouragement for exotic interpretations. Every truly revolutionary astronomical discovery, from the heliocentric theory to black holes to exoplanets, initially faced skepticism from established scientific communities. But history also shows that extraordinary claims, without extraordinary evidence, usually fade into oblivion, leaving behind cautionary tales about the dangers of premature and unfounded speculation. The opportunity to test against real-world data. The convergence of October 15, 2012, offered a precious opportunity to test these competing hypotheses against actual data. If Atlas and Swan were natural comets, following the predictable laws of physics, their behavior during their perihelion passage would have to conform to well-established models of ice sublimation and dust emission. If they represented something more exotic, deviations from the expected behavior would become apparent during their closest approaches to the Sun. The problem of observation. But there was a significant issue. The very glare of the Sun, that makes close solar passages so scientifically interesting, also made them difficult or impossible to observe from Earth during the most critical stages of their solar encounters. Both objects would be obscured from our ground-based telescopes. This forced us to infer what had happened based on their condition as they emerged from behind the Sun, if they emerged at all, leaving a void for speculation. A space for the gap hypothesis. This observational gap created space for speculation to grow, unchecked by data. In the absence of direct measurements, any theory can seem possible. Any interpretation can seem plausible. The silence of October may tell us as much about human psychology as it does about these mysterious cosmic visitors. In conclusion, a scientific opportunity, regardless of which theoretical framework ultimately proves correct. The convergence of Atlas and Swan represented a moment, a true scientific opportunity, whether they turn out to be strange balls of ice or something much stranger. They are expanding our understanding of what exists in the space between stars and what can occasionally find its way into our cosmic neighborhood. The hypotheses we build around them say much about our hopes and fears, as well as about the objects themselves. But perhaps that is as it should be, whether it is a comet or a fortress. or a reply to a message we never knew we sent. The answer could shape how we see our place in this vast universe. Part 6. Discovery and Orbit. A pixel that changed history. The story of Bialas begins with a single pixel, a tiny change in brightness on a CCD detector in the Atacama Desert of northern Chile, July 1st, 2012. Marked the historic moment when this interstellar wanderer finally became bright enough for our automated sky surveys to distinguish it from the background stars which have held their positions for millennia. The Atlas system, the mechanical gatekeeper of the Atlas survey, short for the Asteroid Terrestrial Impact Last Alert System, operates 4 robotic telescopes designed primarily to detect asteroids that could potentially threaten Earth. These mechanical gatekeepers constantly scan the sky, methodically comparing each night's observations with catalogs of known objects to identify anything that moves, brightens, or appears where nothing was before. When the Atlas telescope at Rio Hurtado recorded the first detection of Bialas, the object appeared as just a faint smudge moving against the stellar background. But motion in space tells a story, and within hours of its discovery, orbital calculations revealed something extraordinary. This new visitor was on a hyperbolic trajectory, unbound by the gravity of our sun, the mathematics of cosmic destiny. The mathematics of orbital mechanics divides all celestial bodies into 2 basic, distinct categories. Those that belong to our solar system follow elliptical orbits, eventually bringing them back to where they began in a perpetual cycle, and those that are just passing through, following hyperbolic paths, making a single pass by our sun, and then heading forever into the vast cosmic void. Bialas was definitively of the second kind, marking it as the 3rd confirmed interstellar visitor in human history, journeying from deep space. The orbital characteristics of Atlas tell the story of a journey that began in interstellar space. The orbit possesses an inclination of about 175 degrees relative to Earth's orbital plane, which means it approached our solar system from below, moving in the opposite direction to the motion of the planets. This is an unmistakable sign of an object that formed elsewhere in another star system, with completely different physical conditions, then spent millions of years crossing the void between the stars before reaching our cosmic neighborhood. A discovery nearly missed. The timeline of its detection shows just how regrettably close we came to overlooking this visitor. Interstellar objects approach from random directions in space, often spending months or years in regions of the sky too close to the sun for effective observation from Earth. By the time Atlas was discovered, it had already passed through the outer reaches of the solar system and was beginning its final approach to perihelion. Tracing back its orbital calculations reveals that this wandering object had been in the solar system since early 2022, or possibly even late 2021, gradually brightening as it neared the sun, and began to show the first signs of cometary activity. This late detection illustrates one of the fundamental challenges in detecting interstellar objects. We can only find them when they are bright enough, and favorably positioned enough for our instruments to distinguish them from the background stars. Detailed orbital forecasts. Current predictions characterize the perihelion of Atlas, the moment of its closest approach to the sun, as around May 29th or 30th, 2022, at a distance of approximately 1.35 to 1.4 astronomical units. To put that into perspective, this places the object just inside the orbit of Mars, closer to our star than any previous interstellar object ever observed. The trajectory will take Atlas past Mars on October 3rd, 2022, at a distance of about 30 million kilometers. Although this is a distant flyby in human terms, it is close enough for the sophisticated instruments aboard our Mars spacecraft to potentially observe this visitor during a critical phase, as it approaches the sun at a safe distance. Comet Atlas maintained a safe distance throughout its journey, with its closest approach to our planet occurring at about 1.8 astronomical units, equivalent to about 270 million kilometers. This distance ensured that this visitor posed no threat to Earth, while still being observable with our most powerful telescopes. During favorable observation periods, regarding its size, the size estimates for Comet Atlas remain uncertain, but they suggest a relatively modest nucleus. Observations by the Hubble Space Telescope on July 21, 2022, constrained the object's size to perhaps just a few kilometers in diameter, large enough to generate the observed cometary activity, but much smaller than the spectacular comets that have graced our skies in recent decades. This size estimate comes with considerable uncertainty due to the challenges of observing such distant, faint objects. The brightness that we perceive is the result of sunlight scattered by dust and gas in the comet's coma, which surrounds the nucleus, rather than from the nucleus itself. Determining the actual size requires careful modeling of how efficiently the nucleus reflects sunlight and the amount of material it releases into space. Through complex sublimation processes, the Coordinated International Observation Campaign for Comet Atlas represents one of the most in-depth studies ever conducted on an interstellar visitor. The Hubble Space Telescope provided high-resolution images, tracking changes in the structure and brightness of the coma over time. The James Webb Space Telescope aimed its infrared capabilities at the object in August, revealing details about its chemical composition that would have been impossible to obtain from ground-based observations. The Very Large Telescope in Chile contributed vital spectral data, breaking down the visitor's light into its constituent colors to identify the specific molecules and atoms glowing within its coma. As for unusual chemical discoveries, these observations revealed unusual chemical signatures, including strong nickel emissions without corresponding iron, and cyanogen lines that were prominent. And a dominance of carbon dioxide made Comet Atlas an object of intense scientific interest. And the public's fascination. Many space telescopes continued to track this visitor as it neared its encounters in October. But time was running out for detailed observations from Earth's vicinity, a challenge against time. The combination of increasing distance and an unfavorable solar elongation angle would eventually make ground-based observation impossible, leaving us dependent on any data that our instruments on Mars could gather during the brief flyby. The global coordination, the international cooperation necessary for this observation campaign, illustrates how modern astronomy operates as a global enterprise. Telescopes in Chile tracked the object during nights in the southern hemisphere, then handed over the observations to facilities in Hawaii and the Canary Islands as the Earth turned, bringing the visitor into different viewing zones. Space-based observatories provided continuity through the day-night cycle and atmospheric conditions that could block ground-based observations. What we almost missed. Perhaps the most fascinating aspect of the Atlas discovery relates to what we almost missed. The visitor's faint nature and the initially unfavorable observation geometry meant that, for many months, perhaps even years, it had traveled through our solar system undetected. How many similar objects might have passed through, without ever being bright enough or favorably positioned? Enough for our surveys to find them detection efficiency. The detection efficiency for interstellar visitors depends heavily on their size, composition, and trajectory. Objects that do not produce a significant cometary tail may remain invisible until they are very close to the Sun, while those approaching from certain directions can be obscured by the Sun's glare throughout their journey through the inner solar system. Statistical models suggest that for every interstellar object we detect, tens, or even hundreds, may slip by unnoticed, a glimpse into a larger population. Atlas represents not just a single discovery, but a glimpse into what might be a much larger population of cosmic wanderers that regularly pass through our neighborhood. The current and future status as 10 2002, 12 approaches. Comet Atlas continues its relentless journey toward perihelion. It is now visible to experienced observers. With modest telescopic equipment, its characteristic green glow has become a prominent feature in the autumn sky, a reminder that our solar system is a crossroads for travelers from distant stars. In a final opportunity before it disappears into the sun's glare, Mars holds a prime position. To uncover any secrets this visitor might carry, the European Space Agency has announced preliminary plans to use its Mars-orbiting assets to observe this opportune encounter. In conclusion, it is a race against time. The question is whether our instruments, both on Mars and on Earth, are sophisticated enough to distinguish between the strange and the extraordinary in the short time that remains. To observe this remarkable cosmic wanderer, with each passing day, Comet Atlas moves closer to perihelion, and further from our ability to observe it. The secrets it carries from interstellar space may be revealed in the coming weeks, or they may remain forever hidden within the blinding glare of the sun. Part 7. Strange Colors and Mysterious Chemistry. The language of cosmic light. The universe paints its stories in wavelengths of light and comet. Atlas has been creating an enchanting green masterpiece since its discovery. As this interstellar visitor approaches our sun, its nucleus heats up and begins to release frozen gases that have been locked in ice for millions of years. But the palette emerging from this cosmic artist does not quite match the colors we expect from objects born within our own solar system. The mystery of the green color. The green that has captivated observers around the world stems from a complex interplay of chemistry and physics occurring in the near-vacuum environment of the comet's coma. When molecules are excited by intense ultraviolet radiation from the sun, or by collision processes, they emit light at very specific wavelengths, determined by the delicate quantum mechanical structure of their electron orbitals, responsible for the green emission. The most common culprits are diatomic carbon molecules and cyanogen radicals. Both fluoresce brilliantly when exposed to sunlight. Light Science reported on this phenomenon and discovered the leading candidates for this green light. The problem of precise identification, however, is that while diatomic carbon remains the most likely explanation, based on previous comet observations, the specific molecular species responsible for the color of Comet Atlas has not been definitively confirmed through high-resolution spectroscopy. This distinction is very important because different molecules tell different stories about the conditions under which this visitor formed and evolved. Cyanogen, a beauty born from poison. Cyanogen is a molecule composed of carbon and nitrogen atoms, representing one of the most toxic substances known in chemistry. But it shines with an ethereal beauty when released into the vacuum of space. Its presence in a comet's spectrum provides important clues about the organic chemistry that occurred in the stellar nursery where Comet Atlas originated. The ratio of cyanogen to other carbon-based molecules can reveal details about the temperature and pressure, and the chemical processes that occurred billions of years ago around a distant star that we have never seen. The nickel without iron puzzle. But the green light only represents the most visible aspect of a much more complex chemical story. When the Very Large Telescope in Chile aimed its powerful spectrograph toward Comet Atlas, it revealed molecular fingerprints that challenge our understanding of how these interstellar visitors should behave. The detection of prominent nickel emission lines, unaccompanied by the signatures of iron that usually appear with them, created a chemical puzzle that made researchers reconsider their assumptions about cometary composition, breaking a cosmic rule. In terrestrial samples and most meteorites, nickel and iron appear together, in a ratio that reflects the nuclear processes that create these elements in the cores of stars. Models of cosmic abundance, enshrined in the periodic table, suggest that these elements should appear together in predictable ratios wherever they are found. Comet Atlas seemed to ignore this fundamental rule of cosmic chemistry. Detailed data from the VLT observations, conducted during the comet's approach phase, revealed strong nickel emission at 588 nanometers, a characteristic green line that stood out clearly against the complex background of the cometary emission spectrum. At the same time, sensitive instruments searched for iron emission at equivalent wavelengths and found virtually nothing. The upper limits were so strict that if iron had been present in normal cosmic proportions, it would have been easily detected. Theoretical explanations. A few theoretical explanations have been proposed to account for this chemical anomaly. Nickel-containing organic compounds. Nickel-containing organic compounds stable in the extremely cold conditions of space between the stars could decompose under the influence of solar heat to release nickel atoms into the comet's atmosphere. Space weathering. Space weathering processes, occurring over millions of years, could alter the surface chemistry in ways that affect how different elements are incorporated into the sublimating ices. The broader chemical picture revealed by multiple observation campaigns shows that Comet Atlas is a visitor shaped by very different formation conditions. Compared to objects born within our own solar system, discoveries from James Webb. Observations from the James Webb Space Telescope using the NIRSpec instrument revealed a composition dominated by carbon dioxide, with water vapor playing a relatively minor role in the early stages of the comet's activity. This dominance of carbon dioxide tells a story about formation in a colder, more volatile-rich environment than the region where Earth and the other rocky planets formed. Different formation conditions, different star systems, experience different temperature profiles during planet formation, potentially leading to comets with chemical compositions unlike anything in our Oort cloud or Kuiper belt. An analysis by the European Space Agency of these infrared observations revealed a low water-to-carbon dioxide ratio, observed at a large heliocentric distance, representing typical early activation behavior, where the most volatile ices sublimate before the comet begins its closer approach to the Sun. The molecular production rate as Comet Atlas continues toward its perihelion. The relative contribution of water vapor to the total outgassing increases as the less volatile ices reach their sublimation temperatures. The production rates of various molecular species offer another glimpse into the nature of this unusual object. As Comet Atlas draws nearer to the Sun, the rate at which it produces water vapor, carbon dioxide, and cyanogen, and other species predictably increases as its distance from the Sun decreases, providing evidence of a natural process. These production curves follow the expected sublimation patterns of ices, providing strong evidence that we are observing natural physical processes rather than artificial emissions. Yet, within this framework of predictable behavior, subtle anomalies persist, intriguing researchers. The ratios between the various molecular production rates do not perfectly match models based on comets within our solar system. Contributions from the amateur community. The amateur astronomy community has played a crucial role in documenting these chemical changes over time. High-quality images from experienced observers around the world provide temporal coverage that professional telescopes, with their limited observation time and competing priorities, cannot match. These observations track changes in the comet's color, the development of its tail, and its overall brightness, complementing the detailed spectral studies conducted by major observatories. Amplification on social media. Social media has amplified certain aspects of these chemical mysteries, sometimes turning preliminary scientific findings into sensational claims that go beyond what the data actually supports. The detection of nickel without iron was interpreted by some as evidence of potential industrial processes or a sign of manufacturing, Despite the availability of plausible natural explanations for this phenomenon, the official stance, NASA's official position emphasizes that current observations remain consistent with the natural cometary object, albeit one with unusual yet not unprecedented characteristics. Agency scientists note that other chemical peculiarities is often what is expected for objects formed around other stars, where varying temperatures, pressures, and elemental abundances can create compositions unlike anything familiar in our solar system. Distinguishing between the strange and the extraordinary, the difference between strange and extraordinary remains crucial for interpreting these observations. Strange chemistry, unusual, but explainable through known physical processes, is fundamentally different from extraordinary chemistry, which might suggest an artificial origin. Comet Atlas clearly exhibits strange characteristics, but whether those characteristics cross the threshold to become extraordinary remains a topic of ongoing scientific debate. Historical context provides important insight into these chemical anomalies. Comet 2I Borisov, the previous interstellar visitor studied in detail, showed its own chemical peculiarities, initially baffling researchers. Its carbon monoxide to water ratio was different, significantly from solar system comets, but detailed analysis revealed these differences could be explained by formation in the colder outer regions of its parent star system. Alternative chemical explanations. VLT analysis of Comet Atlas included discussions of alternative chemical pathways that could produce the observed nickel signatures without resorting to exotic explanations. The compound nickel carbonyl, formed through reactions between nickel-containing dust grains and carbon monoxide in the cold interstellar medium, could explain the preferential release of nickel over iron when heated by solar radiation. Time is running out as Atlas continues its approach to perihelion. The opportunities for detailed chemical analysis are dwindling. The heating from the sun, which activates the most interesting chemical processes, also positions the comet at increasingly difficult viewing angles from telescopes on Earth. The final question: what if the flare-up we are observing is not just chemistry awakening under the sun's influence, but protocols being activated according to a deeper design? The molecules themselves do not reveal their ultimate origin. They only shine with the precision of quantum mechanics, which governs all matter, whether natural or a product of intelligence, bridging what we do not yet understand. As Comet Atlas continues its journey towards the sun, what stories does it carry? Written in light and molecules, these stories might tell of the conditions of formation in a distant star system, or perhaps reveal something more profound about the nature of these interstellar travelers. Its captivating green hue and its unusual chemical fingerprint remind us that the universe is still full of mysteries, and that sometimes visitors from distant stars bring questions that we are not yet ready to answer. Ultimately, whether Comet Atlas was a comet or something stranger, it has expanded our understanding of what might exist in interstellar space and what might find its way to visit us. Part 8. The Mars Flyby. A cosmic rendezvous millions of years in the making. October 3rd, 2012, marked a cosmic rendezvous that had been millions of years in the making in the silence of space. On this day, Comet Atlas would fly past Mars at a distance of about 30 million kilometers, close enough for the red planet's fleet of robotic explorers to aim their sophisticated instruments toward this interstellar visitor, and potentially gather the most detailed observations that we could possibly obtain of an object from another star system. To put the distance in context in planetary science terms, 30 million kilometers hardly qualifies as a close encounter. That distance is equivalent to 5 times the distance between the Earth and the Moon, or about 1/5 of an astronomical unit. But in the context of an interstellar visitor traveling on a hyperbolic trajectory at tens of kilometers per second, this represents an extraordinary opportunity for detailed study. During the crucial phase, as the comet approaches the Sun. Observation plans from the ESA, the European Space Agency, announced preliminary plans to coordinate observations using multiple spacecraft, orbiting Mars during this brief window of approach. Each spacecraft carries unique capabilities that could contribute to the overall understanding. These instruments could reveal details about the molecules and atoms being released as the comet warms up under the Sun's influence. Mars Express, now in its third decade of operation around the red planet, offers complementary imaging capabilities and spectroscopic instruments that can contribute to our understanding of this cosmic visitor. Its long-term experience operating around Mars makes it a reliable observation platform. Equipped with the powerful high-rise camera system, it offers perhaps the most compelling observation capabilities, while the comet will be too distant to resolve surface features. High-rise's superior sensitivity and resolution could reveal details about the comet's structure, dust distribution, and tail morphology that Earth-based telescopes cannot see when operating through our planet's atmospheric filter. The unique advantage of the viewing angle, the perspective during the flyby, past Mars offers an advantage that no observation point on Earth can provide. Mars will be positioned at a different angle relative to the Sun and the comet, potentially revealing structural aspects of the coma and tail that remain hidden from our vantage point on Earth. The lack of atmospheric turbulence eliminates the limitations of seeing and absorption effects that constrain ground-based observations, allowing for sharper images and more accurate spectroscopic measurements. Significant technical challenges, however, considerable challenges complicate these observation plans. The Mars orbiters were designed primarily to study the planet below them, not distant objects in deep space. Their navigation systems, communication protocols, and data storage capacities reflect these priorities. This requires careful coordination to redirect the instruments toward a target millions of kilometers away, while still maintaining the primary mission objectives. The detailed scientific goals for these Mars-based observations focus on characterizing aspects of Atlas that remain poorly understood from Earth-based studies. Analysis of the dust structure. Detailed imaging can reveal the size and distribution of dust particles within the coma by analyzing how they scatter sunlight at different phase angles. This information provides important clues about the formation process and evolution of comets. Spectroscopic studies. Spectroscopic observations can constrain the relative ratios of different molecular species, especially during periods of active outgassing. As the comet gets closer to the Sun, this could help solve the mysteries about the unusual chemical composition we have observed. The ion tail and magnetic fields. The shape of the ion tail represents another potential target for observations from Mars, as the interaction between the solar wind and the ionized gases in the comet's coma creates characteristic tail structures, aligned with the direction of the local magnetic field from Mars's unique vantage point. These features of the ion tail could reveal details about the comet's gas production rate and the local space environment that we cannot observe from Earth. The urgency of the timing of the Mars encounter adds urgency to these observation plans. Atlas will experience increasingly intense solar heating as it approaches its late October perihelion, potentially triggering its most vigorous outgassing activity. Throughout its entire journey through our solar system, the Mars flyby occurs just as this activity is reaching its peak, opening a window into cometary physics that may not repeat for many decades or even centuries. Practical limitations. But practical limitations constrain what even the most sophisticated instruments on Mars can achieve. The distance of 30 million kilometers means that Atlas will appear as just a point of light to most cameras on the orbiting spacecraft. Detailed studies of the nucleus structure or precise mapping of the coma remain beyond the resolution limits of current Martian orbital assets. Communication challenges. The communication delay between Earth and Mars further complicates observation planning. In real time, radio signals take 424 minutes to travel between the planets, depending on their relative positions in their orbits. This means that observation sequences must be pre-programmed and uploaded to the spacecraft's memory with limited ability for parameter adjustments, based on real-time developments in the comet's behavior. Environmental factors, atmospheric conditions, and dust storms on Mars are another unpredictable factor that can affect the quality of observations. While large, global dust storms are rare, local and regional dust events can reduce visibility and contaminate sensitive instruments. Mission planners must balance the desire for optimal observation times with the unpredictable weather patterns on Mars, which can compromise data quality. The issue of data transmission and data return times add another layer of complexity to these observations. Mars orbiters typically download collected data to Earth during scheduled communication windows, which may not align optimally with the brief flyby period. Some of the most interesting observations may not reach Earth until several days or weeks after the encounter, limiting our ability to coordinate follow-up studies or share preliminary results with the global astronomical community. Our best opportunity. Despite these challenges, the flyby past Mars represents our best chance to study an interstellar visitor during its most active phase. Earth-based telescopes will soon lose sight of Atlas as it disappears into the sun's glare, making the Mars observations potentially our last clear view of the object until it re-emerges from behind the sun months later, if it re-emerges at all. Verifying theories. The scientific results from these observations could provide crucial tests for competing theories about the nature of Atlas. Natural comets undergoing thermal processing near the sun will exhibit predictable dust patterns and observable gas release through changes in the coma's brightness and tail morphology. Any significant deviations from these expected patterns could hint at more exotic explanations for the mysterious visitor's behavior. Realistic expectations, however, it is important to maintain realistic expectations about what these observations can and cannot reveal. The flyby past Mars will not involve any direct contact or close approach. The visitor will be millions of kilometers away. Throughout the encounter, no samples will be collected, no surface features will be resolved, and no details of the internal structure will be gathered. This remains a remote observation, albeit from an advantageous position, a proof of concept for the future. The observation campaign also serves as a proof of concept for future studies of interstellar visitors. The techniques developed and tested during the Atlas flyby could inform observation strategies for potential future visitors, leading to more sophisticated international coordinated efforts to study these rare cosmic travelers. Contingency planning recognizes that technical failures, communication issues, or unfavorable observation geometries could limit or eliminate useful data from the encounter. Backup observation strategies using Earth-based telescopes provide some redundancy, although they are affected by increasing sunlight and atmospheric limitations. The brief time window, as the Mars approach timeline draws near, compresses the most scientifically valuable observation phase into just a few hours or days around the closest approach. During this brief period, our robotic ambassadors orbiting the red planet will turn their electronic eyes towards a visitor from another star system, attempting to capture any secrets it might reveal during its journey through our cosmic neighborhood. Epilogue. Listening to the cosmic static. If Mars could eavesdrop on the electromagnetic spectrum during those crucial hours, what stories might it intercept? In the static of space, the instruments will listen with the patience of machines and the curiosity of their creators, hoping to decode any message that might be written in the light of a wanderer from the stars. But first, the visitor must complete its appointment with the fourth planet of the solar system. We carry with us every mystery it holds, slipping past the watchful eyes of the sentinels. Our Mars heads toward its final destination, beyond the blinding light of the sun. October 3rd, 2012 may be remembered as the day we had our last clear view of Bialas before it disappeared into the void. An observation carrying answers that we might have to wait months for, or perhaps forever to receive. Part 9, Swan Ride, the New Giant. The arrival of the giant. While Bialas had captured the attention as a strange visitor from interstellar space, another cosmic traveler quietly prepared to capture the spotlight. Comet C, 2015, G2, also known as Swan Ride, after being discovered in the data of the Solar and Heliospheric Observatory, emerging from the depths of our solar system to become one of the most spectacular cometary displays visible from Earth in recent years. The story of discovery. The story of its discovery begins with the patient dedication of an amateur astronomer who spent hours examining images from the SWAN instrument, searching for the telltale signs of new comets hidden in the sun's glare. On September 11th, 2015, his persistence paid off when he spotted an unusual brightening in the data that was later confirmed to be a previously unknown comet approaching its closest point to the sun. The SWAN instrument, the Comet Hunter, unexpectedly, the SWAN instrument, the Solar Wind Anisotropies instrument on the spacecraft, SOHO, acted as an unexpected comet hunter, although it was primarily designed to study the solar wind's interaction with the interplanetary medium by mapping the distribution of hydrogen atoms created when water molecules are broken apart by the sun's ultraviolet light. SWAN can detect cometary activity that remains invisible to conventional telescopes, especially for objects too close to the sun to be safely observed from the ground. The Hastu effect and the sudden appearance. The appearance of the comet. Swan Ride's emergence from solar conjunction illustrates one of the fundamental challenges in discovering comets, long-period objects that often take many months to approach the sun, from directions with small angular separations. From our star as viewed from Earth. The Hastu effect is named after the Austrian astronomer who first described it, explaining why many spectacular comets seem to appear suddenly in our skies, fully formed and already active. The comet's official designation is C, 2015's 2. Following the systematic naming convention of the International Astronomical Union, the letter C indicates a long-period comet, likely originating from the distant Oort cloud that surrounds our solar system. 2015 marks the year of its discovery, while CES2 indicates it was the second comet discovered in the second half of September, bright and its observability until mid-September of 2015. Comet Swan Rye was visible to the naked eye for observers in dark skies, shining at around magnitude 6, the threshold at which objects become visible without optical aid under ideal conditions, but unlike many other comets that reach peak brightness and then fade. This visitor continued to brighten as it emerged from its encounter with the sun and began moving toward its closest point to Earth. The astronomical picture of the day feature on September 16th highlighted Swan Rye as a newly discovered comet visible with binoculars, noting its rapid increase in brightness and the spectacular development of its tail, which had made it a favorite target for astrophotographers around the world. The comet's position near the bright star Spica in the constellation Virgo provided a point of convenient reference for amateur observers trying to locate it in the sky. A multitude of observation reports from experienced comet watchers began to record the length of a tail extending up to 2 degrees across the sky, about 4 times the apparent diameter of the full moon. The tail structure and analysis of these measurements though approximate due to the subjective nature of visual comet observation, and the processing techniques used in digital images revealed a tail structure stretching for millions of kilometers. Physical length, orbital characteristics. The comet's orbital characteristics tell the story of a visitor from the outer edge of our solar system. Unlike Comet Atlas with its interstellar orbit, which was hyperbolic, Swan-Rye followed an extremely elongated ellipse, taking it from the icy regions beyond the orbit of Neptune to as close as half an astronomical unit to the Sun. This represents a journey spanning many decades or centuries, during which time the comet remained frozen and inactive until the solar heat created the spectacular display that we observed on this day. Perihelion and Earth approach. Perihelion occurred on September 12, 2015, when comet Swan-Rye reached its closest point to the Sun at about 0.5 astronomical units, about one-half the distance between the Earth and our star. This close encounter with the Sun caused the comet to heat up intensely, vaporizing its surface ice and releasing dust and gas, creating its visible coma and tail. The comet will make its closest approach to Earth on October 21, 2015, when it will pass within 0.217 astronomical units of our planet, approximately 40 million kilometers, which creates a favorable viewing angle to place Swan-Rye in its most accessible position for detailed observation during the same period that Comet Atlas approaches its perihelion. Brightness forecast. Current brightness estimates indicate that Swan-Rye reached a magnitude of 6.7 in mid-September, making it easily visible with binoculars, and beginning to be visible to the naked eye for observers under excellent viewing conditions. The continued brightening suggests the comet could reach a magnitude of 4 or 5 at its closest approach to Earth, potentially becoming one of the brightest comets visible in 2015. Viewing conditions. The southern hemisphere offers the most favorable viewing conditions for the comet Swan-Rye during its evening appearance, although northern hemisphere observers can still see the comet low in the western sky after sunset. The comet's position relative to the ecliptic plane and its motion relative to Earth create changing viewing angles, affecting its observability. Throughout its observation window, global observation efforts. Amateur astronomy networks worldwide have mobilized to document the evolution of comet Swan-Rye, creating a real-time observational database that complements professional astronomical studies. High-quality images from experienced astrophotographers reveal intricate details in the tail structure, including potential disconnection events, where magnetic field interactions temporarily separate portions of the ion tail from the main cometary body. Orbital uncertainty. However, significant uncertainties remain in Swan-Rye's orbital parameters due to the relatively short observation arc available. Since its discovery, comets can be subject to non-gravitational forces caused by outgassing, which subtly alters their trajectories, making it difficult to make precise long-term predictions until more observational data is available. Minor Planet Center. Continuing to refine the orbits as new astronomical observations arrive from observatories around the world. These measurements will ultimately determine whether Swan-Rye is following a closed elliptical orbit that will eventually bring it back to the inner solar system, or whether gravitational perturbations during this passage will push it permanently into interstellar space. Safety assessment. Safety assessments indicate that there is no threat to Earth from the comet's current trajectory. The closest approach distance is 0.27 astronomical units, maintaining a comfortable safety margin, while also providing an excellent opportunity for detailed study of this visitor from the outer solar system. Standard precautionary procedures. Continue to monitor the comet's orbit for any unexpected changes that could affect these predictions. Educational and outreach impact. The comet's rapid development and its spectacular appearance have made it a favorite subject for public outreach and educational activities. Astronomy clubs and planetariums around the world are integrating Swan Rai into their programs, using its visibility as an opportunity to educate audiences about comet formation, solar system structure, and the dynamic processes that shape our cosmic environment. Professional research. Professional observatories are beginning to add Swan Rai to their target lists for spectral and photometric studies, while most telescope time is still allocated to Comet Atlas due to its interstellar origin. Swan Rai offers a valuable opportunity to study the composition and behavior of objects from the outer regions of our solar system. Comparison with Comet Atlas. The timing of Swan Rai's appearance is nearly simultaneous with Comet Atlas's passage through our inner solar system, creating an unprecedented opportunity to compare two very different types of objects. One, an interstellar body, one from our own Oort cloud, undergoing similar physical processes under similar thermal, solar conditions, allowing researchers to examine how the formation environment affects cometary behavior. If Atlas represents a scout exploring our cosmic neighborhood, why did Swan arrive like a city-sized harbinger announcing something far greater? The universe rarely provides such convenient juxtapositions for comparative study, making October of 2015 a month that could reshape our understanding of what moves through the spaces between and within star systems. Part 10. Technical speculation, propulsion, shielding, and trajectories. The boundary between the strange and the engineered is often blurred in the realm of speculative astronomy, where observations that are unusual can inspire extraordinary theories about what might be possible in a universe filled with intelligence we have yet to recognize. Atlas and Swan are two current features that, while explainable by natural processes, also invite consideration of more provocative alternatives, if only as thought experiments in the physics of motion, orientation, and controlled energy release. Propulsion mechanisms and detection. Let us first consider the question of propulsion. Natural comets follow orbits that are determined entirely by gravitational mechanics, their paths through space governed by the inverse square law, and the initial conditions of their formation or ejection from distant star systems. Any true propulsion system would reveal itself through measurable deviations from these predicted trajectories, constant acceleration vectors, attitude changes, or course corrections, all violate the principles of ballistic motion, a directed plasma engine, operating by expelling ionized gas at high velocity, would produce observable signatures in both its trajectory and its electromagnetic spectrum of the host object. The exhaust would glow at specific wavelengths, determined by the composition and temperature of the ejected material. More importantly, the thrust would produce changes, measurable in the orbital parameters, accumulating over time, into clear violations of Keplerian motion. Atlas exhibits none of these characteristics. Its hyperbolic trajectory follows the expected path of an object, unbound by the sun's gravity, with a brightness and spectral variation that correlates predictably with decreasing heliocentric distance. The outgassing observed by our most sensitive instruments seems perfectly consistent with natural sublimation processes driven by solar heating. The timing and coincidence, the precision of its arrival, near Mars and Earth within a narrow window, coinciding with two close approaches of Swan Rai, challenge statistical expectations in ways that keep theoretical possibilities alive. If coordination rather than coincidence explains this convergence, it would require propulsion systems operating with such subtlety that they would be undetectable by our current observational methods. Electromagnetic shielding. Electromagnetic shielding is another area where natural phenomena could conceal artificial processes. Natural comets develop a plasma sheath as the solar wind interacts with ionized gas. In their expanding comas, These interactions create complex magnetic field structures, deflecting charged particles and shaping the characteristic anti-sunward direction of the ion tail. An active electromagnetic field system would likely look very similar to these natural plasma interactions, differing only in the degree of control and directionality it could impose on the surrounding charged particle environment. The key difference would lie in detecting field configurations with no apparent natural function. Magnetic structures optimized for communication, energy harvesting, or radiation shielding, rather than simply deflecting the solar wind. Current observations show that the ion tails behave exactly as expected from the solar-wind interaction of a natural comet. The James Webb Space Telescope and ground-based spectrographs have detected no anomalous electromagnetic signatures, no coherent radio waves, and no evidence of controlled field generation beyond what solar wind physics naturally creates around active comets. Patrol and surveillance models. The orbital mechanics of scheduled patrol routes would require patterns of return visits or systematic coverage, distinguishing artificial trajectories from the random encounters expected from natural interstellar wanderers, or long-period comets from the Oort cloud. Worlds could disguise themselves as single objects, even if they follow closed elliptical orbits. Since their periods often exceed recorded human history, the actual patrolling behavior would eventually be revealed through repeated appearances at predictable intervals, the synchronous appearance of multiple objects, or orbital changes that serve a strategic purpose rather than a purely gravitational one. 3 confirmed interstellar visitors have been detected since 2017. Oumuamua, Borisov, and now Atlas show no evidence of a systematic distribution or coordinated activity. The automatic activation hypothesis, in response to our signal hypothesis from Avi Loeb, offers a fascinating thought experiment on the possibility that our electromagnetic leakage into space could have triggered an automated response from dormant surveillance systems distributed throughout our galactic neighborhood. This scenario would explain the temporal coincidence between our technological development and the arrival of these unusual visitors. However, NASA and ESA maintain that the current observational data remains consistent with natural explanations, despite their unusual characteristics. The agencies emphasize that extraordinary claims require extraordinary evidence, and the observed chemical signatures, orbital mechanics, and behavioral physics in both Atlas and Oumuamua fall within the range of natural cometary phenomena, albeit at the more exotic end of that range. The chemical analysis observing nickel without iron in Atlas illustrates how unusual chemistry can be interpreted through both natural and artificial lenses. Industrial processes can selectively concentrate certain elements or isotopes, creating characteristic signatures in their emissions, or waste streams. But the VLT analysis includes a detailed discussion of natural pathways, nickel-carbonyl chemistry, space weathering effects, and selective sublimation processes that could produce similar chemical fingerprints without invoking a technological origin. The changes in color and brightening behavior represent another area where natural and artificial explanations compete. Comets frequently exhibit non-linear light curves as different volatiles reach their sublimation temperatures at varying heliocentric distances. This creates the appearance of dense activation events, which might suggest active propulsion systems, whereas in reality they reflect the physics of ice sublimation in a vacuum. Distinguishing between natural outgassing and artificial emissions requires an analysis of thrust vectors, acceleration profiles, and energy budgets that exceed what random sublimation processes could produce. Current observations show that the brightness and spectral changes correlate precisely with the expected behavior of sublimating ice under the influence of increasing solar radiation flux. Technosignatures and the possibility of detection. The hypothetical signs of a true engineering construct could be detected through several observational channels. constant propulsive acceleration would accumulate into measurable orbital perturbations over time. Attitude control systems would create periodic variations in brightness, or spectral characteristics as different surfaces or components face toward or away from the sun. Coherent electromagnetic radiations would stand out against the natural radio background of space. Coordinated international monitoring efforts have searched for precisely these types of anomalous signals using radio telescopes, radar systems, and sensitive photometers. Successor facilities to the Very Large Array, Arecibo, and other major radio observatories have conducted searches systematically for artificial signals from any visitors. No coherent transponder signals, no structured electromagnetic emissions, and no evidence of electronic devices in operation has been detected. Radar observations conducted by several facilities have also yielded null results, although the great distance makes detection very difficult, even for the most powerful planetary radar systems. The lack of a strong radar signal is consistent with a natural cometary surface, composed of a low-density mixture of ice and dust, rather than a metallic or highly reflective artificial structure. Thermal and energy analysis provides another test of an artificial versus natural origin. Spacecraft, or other artificial objects, often display thermal signatures different from those of natural bodies, due to their internal heat sources, thermal regulation systems, or exotic materials. Both Atlas and Swan exhibit infrared emission profiles consistent with natural solar heating of a mixture of ice and dust. Energy budgets for different technological scenarios also reduce the reliability of quantitative analysis. Interstellar travel requires enormous amounts of energy, whether for acceleration, life support, or communication across galactic distances. Objects capable of making such journeys would likely display signs of advanced energy systems, which remain conspicuously absent in our observations. Scientific response protocols. The procedures for mission escalation exist within the international astronomical community to respond to truly anomalous discoveries. If an independent observatory were to detect clear evidence of artificial signatures, structured signals, non-gravitational acceleration patterns, or impossible chemical compositions, coordinated follow-up campaigns would mobilize resources from NASA, ESA, and other space agencies to conduct in-depth studies. These protocols were not activated for either Atlas or Swan, indicating that despite their unusual characteristics, both objects remain within the bounds of natural phenomena. As understood by mainstream astronomy, the scientific consensus continues to favor exotic, but natural explanations for their observed properties, the limits of detection. However, the failure to detect artificial signatures does not definitively prove a natural origin, especially for hypothetical technologies that operate beyond our current detection capabilities. Advanced civilizations might use propulsion systems, communication methods, or material science that generate signatures we lack the sophistication to recognize or interpret. This cognitive limitation, our inability to prove the absence of artificial features, leaves room for continued speculation about technological interpretations. The gap between what we can observe and what might theoretically exist allows for scenarios that cannot be disproven with our current instrumental capabilities. The psychological appeal of technological explanations reflects deeper human desires to find purpose and intelligence in natural phenomena, which could otherwise be mere coincidence, such as the precise timing of both visitors' arrivals, their unusual characteristics, and their coincidental appearance in our solar system, during a period when human technological progress creates narrative patterns, which our pattern-seeking minds interpret as potentially significant. Statistical analysis of interstellar visitors suggests that the apparent concentration of unusual objects in recent years may represent observational selection effects, rather than a true increase in visitation frequency. Advances in detection capabilities. Our detection capabilities have improved significantly over the last 10 decades, making us more likely to notice objects that might have passed through, undetected in previous eras. 3 confirmed interstellar visitors have been detected since 2017, 1 Oumuamua, 2 Borisov, and 3 Atlas. Each object exhibited initial characteristics that puzzled researchers, but were eventually explained by natural laws. After detailed analysis, this history suggests that anomalous properties do not necessarily imply an artificial origin, even if those properties challenge existing theoretical frameworks. Computer simulations of interstellar object trajectories suggest our solar system should receive natural visitors at a rate roughly consistent with current observations, assuming reasonable estimates for the population density of ejected objects in our local galactic neighborhood. The timing and characteristics of recent visitors fall within the expected parameter space for natural interstellar wanderers. Invisible technology and natural mimicry. The possibility remains that a small fraction of detected interstellar objects could represent technology so sophisticated that it perfectly mimics natural phenomena, whether by design or as a necessary consequence of advanced engineering operating within, rather than against, the laws of natural physics. Such technology would be nearly indistinguishable from natural objects with current observational methods. Perihelion test and observational limits. The ultimate test for these competing hypotheses may come during the October solar encounters, when both visitors will experience their most intense heating and may reveal features hidden during their cooler approach phase, if they are artificial systems. The stress of passing through perihelion could trigger reactions or events, distinguishing these from purely natural behavior. Ground-based telescopes will lose sight of both objects during their closest solar approaches, creating an observational gap during the most scientifically critical phase. This blind spot in our coverage means that the most definitive evidence for or against possible technological explanations might emerge precisely when we are unable to observe. Observations from Mars during 3 flybys, 3 out of 10, are our best chance to maintain surveillance during this critical phase, although the limitations of existing Mars orbiters restrict what can be detected. Even under optimal conditions, the instruments on these spacecraft were designed for planetary science, not for detecting anomalous phenomena during the passage of interstellar objects. The philosophical takeaway is this: if there are indeed machines hiding among these cosmic wanderers, detecting them would require observational capabilities and analytical technique far beyond the limits of current astronomical practice. The distinction between sufficiently advanced technology and natural phenomena might be more subtle than our current scientific frameworks can reliably discern. The question that arises from this analysis is not whether we have found evidence of artificial visitors, but whether we would recognize that evidence if it were present in forms that lie beyond our current understanding of what technology looks like. When viewed across interstellar distances and millions of years of operation, if there were a machine masquerading as a comet, what would we actually see through our telescopes? Perhaps exactly what we are seeing: objects that challenge our understanding while appearing natural, plausibly enough not to trigger the demand for extraordinary evidence that extraordinary claims require. The universe keeps its secrets very well, revealing them only to observers subtle enough to ask the right questions, and patient enough to accept that some answers may lie beyond our current reach. Part 11. A common purpose, finding a pattern in the coincidences. What do they have in common? On the cosmic stage, coincidences become conspiracies, and timing transforms into a choreography as the human mind attempts to find patterns in the cosmic chaos that surrounds our small world. 2 visitors, arriving weeks apart, exhibiting characteristics that are complementary and following convergent orbits toward our sun. Within the same narrow time frame, would begin to look less like random encounters, and more like the coordinated elements of a grander design, if one allows the imagination to fill the gaps where data is silent. The depot and scout hypothesis. Consider the possibility that Swan serves as a mobile depot, while Atlas acts as an agile reconnaissance probe within this hypothetical framework. The vast coma with its long, expansive tail would not be a natural block of ice, but rather a sophisticated logistical platform. Its apparent volatility conceals controlled resource management and communication systems, smaller and more maneuverable. Atlas would act as an advanced scout, gathering information about the characteristics of our solar system and reporting back to the larger base. This depot and scout configuration would explain several puzzling aspects of their observed behavior. The precise timing and trajectory of Atlas could reflect intentional navigation to predetermined coordinates, where Swan would be positioned to receive data, transfer resources, or provide maintenance support. Chemical signatures and controlled emissions. The chemical signatures we interpret as unusual outgassing could, in fact, be controlled emissions, fuel transfers, atmospheric processing, all byproducts of technological systems operating under extreme thermal stress. The natural celestial body takeover hypothesis. Other interpretations suggest that both objects could be natural celestial bodies that have been repurposed, taken over by an ancient surveillance network scattered throughout our galactic neighborhood. Instead of purpose-built spacecraft, they might be hijacked asteroids and comets, their surfaces or interiors modified to serve as platforms for automated systems that activate when specific conditions are met, such as detecting electromagnetic radiation from developing technological civilizations. This hitchhiker scenario would explain why both visitors exhibit characteristics that still just barely fall within the realm of natural phenomena. Any civilization sophisticated enough to establish an interstellar surveillance network would likely prefer stealth over detection, using camouflage and mimicry to avoid triggering defensive responses from the species they encounter. Converting natural objects into technological platforms provides the perfect cover, allowing artificial systems to hide in plain sight among the countless rocks and ice drifting through interstellar space. With the Sun as an energy hub, the star itself could serve as more than just a gravitational focal point. For these operations, solar radiation provides an endless source of energy for systems designed to harness electromagnetic radiation, while the solar wind creates a dynamic plasma environment that could support exotic physics far beyond our current understanding. These streams of ions flowing from our star could be both a means of communication and a power source for technologies operating on principles we have yet to discover. The concept of a galactic surveillance network, these phantoms of the grid, envisions networks of nodes placed in optimal locations within star systems, monitoring the development of planetary environments and the emergence of technological species. The Sun's gravity well creates natural focal points, where information from distant sensors can be aggregated, processed, and relayed to even more distant monitoring stations. Our convergence in October of 2015 could represent a routine data collection and relay operation, the hunt and harvest scenario, a predator and harvester dynamic, offers a more ominous interpretation for this temporal coincidence. If Bay Alas represents a predatory system tasked with identifying and neutralizing emerging threats, then Suanrai could serve as a designed resource extraction platform to process any materials gathered by the predator. The difference in scale between the agile scout and the massive processor would reflect their specialized roles in a larger campaign that views our solar system as either an opportunity or a threat. The images emerging from this theoretical framework paint scenes of small courier ships spiraling inward toward a rendezvous point, while larger structures unfold their collection and processing systems to prepare for any materials or information the scout ships bring back. The apparent cometary activity we observe could be masking far more purposeful operations, harvesting energy, transmuting matter or constructing the necessary temporary infrastructure to support extended operations within our sphere, bordering on speculation. These scenarios exist purely in the realm of imagination, unsupported by direct observational evidence but compelling enough to capture the human imagination. This is precisely because they provide a narrative structure for phenomena that might otherwise seem random and meaningless. The human mind resists random coincidence, preferring explanations that invoke intention and design, even when those explanations require extraordinary leaps beyond the available data. The tension between coincidence and orchestration reflects deeper philosophical questions about the nature of intelligence in the cosmos and our ability to recognize it when encountering it in unfamiliar forms. If advanced civilizations routinely operate using technology that mimics natural processes, how would we ever distinguish between a genuinely natural phenomenon and a sufficiently sophisticated artificial system? The October temporal structure. The October events provide factual data and a temporal structure around which speculative narratives can be built. September 12th, perihelion of B Atlas. October 3rd, Mars flyby of BI Atlas. October 29th, perihelion of Swan. October 21st, closest approach to Earth, creating a sequence of coordinates in space and time that could be a cosmic coincidence or a carefully planned arrangement. Mythological and cultural parallels from human history provide templates for interpreting such dual appearances as omens or harbingers of great change. Every civilization on Earth has its legends of visitors from the sky, the storm before the transition. Across historical epochs, lights in the sky have heralded the rise of empires, the fall of dynasties, or the emergence of new forms of knowledge and power. Perhaps Atlas and Sonrai represent a modern expression of these archetypes. The message and the response, a recurring refrain, echoed throughout our investigation. Is it a comet, a fortress, or the answer to a message we never knew we sent? Takes on new meaning when applied to paired visitors instead of singular anomalies. If one represents the message and the other the reply, their convergence could mark the completion of an exchange of information that began when our radio signals first leaked into space many decades ago, moving from observation to speculation. But it is important to set our bearings at this point in our narrative journey. We have crossed the threshold into pure speculation, leaving the anchor of observational data behind to enter the uncharted waters of imagination and possibility. The facts that shape our investigation, the October timeline, the chemical signatures, the orbital mechanics, continue to favor natural explanations, even as they inspire more fantastical interpretations. The question of a shared mission assumes coordination where none has been proven. It assumes purpose when coincidence remains the simpler explanation, and it assumes intelligence when natural processes provide perfectly adequate explanatory frameworks. These assumptions reflect a human psychological need for meaning and order, as much as they reflect the facts of the scientific puzzle presented by the interstellar visitor's behavior, invisible technology, and detectability. However, the possibility cannot be entirely dismissed that some form of advanced technology could be so sophisticated that it operates indistinguishably from natural processes, whether by design or as a necessary consequence of engineering that works with, not against, the fundamental laws of physics. Such technology would require detection methods and analytical frameworks far beyond our current scientific capabilities. The final perihelion test, the ultimate test of these shared purpose scenarios, may come in the upcoming solar encounters, when both objects will undergo their most intense heating and potentially reveal features that were hidden during the colder phases of their approach. If there is coordination between these objects, it might manifest in the tension and opportunity of the perihelion passage. When energy and communication demands reach their peak, the observational gap created by the sun's intense glare during these crucial phases means that the most definitive evidence for or against coordinated behavior may arise, precisely when our instruments cannot observe. An open ending, the hidden weeks. We might emerge from the silence of October with refined data on natural cometary processes, or we might find ourselves faced with evidence that challenges our fundamental assumptions about what moves in the darkness between the stars. If they share a mission, what mission requires both a scalpel and a factory? The answer may be written in the fire of our sun during the coming hidden weeks, as the two cosmic visitors dance their final steps within humanity's view, before disappearing into the archives of memory and speculation. Part 12. The Relay Hypothesis. A cosmic data drop in the realm of speculative astronomy, where imagination meets physics. Few scenarios capture a sense of cosmic purpose like the Relay Hypothesis. The idea that Comet Atlas acts as a data courier, while Comet Swan functions as a processing and transmission hub, converging on our sun to complete an information exchange that has been in preparation for years or even decades. Comet Atlas, the interstellar messenger. Imagine Comet Atlas as a messenger from interstellar space, carrying compressed archives of observations gathered throughout its long journey through our galactic neighborhood. Its modest size and agile orbit suggest an optimization for speed and maneuverability rather than for bulk data storage. But even a small object can hold a vast amount of information. If encoded with sufficiently advanced storage technologies, the unusual chemical signatures we observe might not be natural outgassing, but rather a controlled process of data transfer, with information being inscribed onto physical substrates. As the transport vessel approaches the designated point, Sony Rai, the data processing center, the coordinates for Rendezvous Point Sunrise emerge from the outer edge of our solar system, presenting the supplementary profile of a data center designed to handle and relay massive-scale operations, and its impressive tail development could conceal sophisticated satellite receiver arrays and optimized transmission systems to operate in the harsh conditions found near a stellar environment. The apparent cometary activity could camouflage directed energy beams, plasma control systems, or exotic communication technologies that operate by manipulating solar-wind interactions, with the sun being the third crucial element. The sun itself becomes the third crucial element in this hypothetical relay operation. Our star represents the most powerful energy source within a range of hundreds of astronomical units, capable of powering systems that could not operate on mobile power sources alone. But the sun provides more than just raw energy. It also creates a unique physical environment where effects like gravitational lensing, magnetic field interactions, and plasma dynamics could enable communication technologies to operate based on principles beyond our current understanding. Gravitational lensing and long-distance communication. Gravitational lensing provides a potential mechanism for long-distance communication using stellar-scale infrastructure. Einstein's theory of general relativity predicts that massive objects like stars can focus electromagnetic radiation, creating natural telescopes capable of detecting signals from immense distances. A civilization sufficiently advanced could place relay stations at the focal points of gravitational lenses throughout the galaxy, using stars as amplifiers for a network of communication that could span interstellar distances. The plasma environment and exotic possibilities. The plasma environment surrounding our sun presents another set of possibilities for exotic physics applications. The solar wind carries charged particles throughout the solar system, establishing currents and magnetic field structures, which could be manipulated by advanced technologies. Imagine systems that write information directly into plasma streams, encoding messages in the magnetic fields. The configurations glide past planets and into interstellar space, a visual representation of data transmission, a visual representation of this hypothetical data transfer, painting scenes of an industrial scale, concealed by natural phenomena, vast collection surfaces, disguised as clouds, of dust and gas, harvest solar radiation with an efficiency that makes photosynthesis obsolete. Memory storage systems write information into crystalline matrices that can survive interstellar radiation and extreme temperatures. Fortresses bathed in ionic fire, while terabytes of compressed data flow between systems, operating at the intersection of matter and energy. The energy requirements are immense. The concept of harvesting sunlight for energy-intensive data operations reflects the colossal energy demands that any interstellar communication system would face. Transmitting a signal across galactic distances demands an energy cost beyond the capacity of even star-scale resources. The convergence of 2000 and 215 might represent the optimal time window when solar activity, planetary alignments, and the positions of receiving stations facilitate maximum data transmission efficiency. Earth's radio bubble, provides the trigger for this entire hypothetical operation. Since the year 1920, our planet has been emitting electromagnetic radiation into space at an ever-increasing rate, creating an expanding sphere of artificial signals, which now extends about 100 light-years in all directions. To any monitoring system located within this bubble, our radio waves represent clear evidence of the emergence of technological intelligence, a signal handshake that could activate dormant relay networks, long established for this very purpose. The temporal correlation between our technological development and the recent arrival of the interstellar visitors. The anomaly takes on a new meaning. In this context, if monitoring systems automatically detected our first radio signals many decades ago, they would have needed time to dispatch delivery systems from distant staging areas, navigating interstellar space, and coordinate with local relay infrastructure. The current wave of visitors could represent the response phase of a communication protocol initiated by our own electromagnetic radiation. Observed reality, however, intrudes upon these imaginative scenarios with the persistence of observed fact. We have not detected the narrow-band radio emissions that any true interstellar communication system would likely produce. No anomalous accelerations have been measured that might indicate controlled propulsion or attitude adjustments. The chemical signatures and physical behavior of both objects remain within the bounds of natural cometary phenomena, albeit at the most exotic end of those bounds. NASA's official position continues to emphasize that current observations favor natural explanations, rather than artificial ones for both visitors. The agency's scientists note that extraordinary claims require extraordinary evidence, and despite their unusual characteristics, neither Oumuamua nor Borisov has shown signs that definitively exceed what natural processes could produce under the right conditions. The question of origin, the question of if they are real, who sent them, opens up avenues of speculation that reveal more about human psychology than about the cosmic visitors themselves. Perhaps they represent messages from our own future, sent back through some manipulation of space-time, allowing information to travel backward in both space and time. Perhaps they originate from parallel evolutionary lines that achieved interstellar travel millions of years ago, and have been monitoring the development of intelligence throughout our local galactic neighborhood. Alternative scenarios posit both objects as components of an ancient automated network established by civilizations that achieved interstellar travel long before Earth formed and have since vanished, leaving only their monitoring and communication infrastructure behind. We are not dealing with active intelligence, but with fossils, the technology of species that transcended or self-destructed long ago, leaving behind automated systems that continue to execute their programming. long after their creators are gone. Physics and practicality. The practicality of any interstellar relay hypothesis involves energy budgets, and the physics of communication strain credulity when one quantitatively analyzes the broadcasting of coherent signals across interstellar distances, requiring energy costs measured as a significant fraction of a star's output. Even receiving such a signal would require antenna arrays with an effective aperture equivalent to a planetary diameter. The infrastructural requirements for an interstellar communications network truly exceed the industrial capacity of most imaginable civilizations. Granted, these limitations only apply to technology, based on humanity's current understanding of physics. Technical civilizations that have mastered interstellar travel may operate by principles that render our concepts of energy and communication obsolete, like smoke signals to a user of a fiber optic network. What seems impossible with 20th century physics may be commonplace for species that understand 21st century physics, just as our current capabilities would seem magical to observers from earlier technological eras. Narrative satisfaction and scientific reality. The relay hypothesis offers narrative satisfaction by transforming random cosmic encounters into events of information gathering and communication. With a purpose, it suggests that humanity has crossed some threshold of technological development, making us worthy of attention from the galactic intelligences that monitor emerging species. It implies that we are not alone and not ignored, that our development is being observed, and perhaps guided by forces operating on a scale we can barely imagine. But it also requires us to accept extraordinary claims based on evidence that remains stubbornly mundane, despite its unusual characteristics. This hypothesis requires coordination where none has been proven, purpose when coincidence offers simpler explanations, and intelligence when natural processes provide perfectly adequate theoretical frameworks, a theory to understand the observed phenomena. The October Experiment. The convergence on October 15, 2002, will provide critical tests for any transition. Hypothesis. If the data transfer truly occurs between our visitors, it will manifest during their closest approach to the sun, when their energy peaks, and communication windows are optimized. The challenge lies in distinguishing between the natural activity of a comet and the signs of an active information processing system, operating under extreme conditions of heat and radiation. What would happen if the handover is completed, while our telescopes are blind? Hidden behind the sun's glare, we are in the most critical phase of this hypothetical campaign. The open-ended conclusion to the silence of October. We might emerge from the October silence with nothing more than sophisticated measurements of ice, sublimation, and dust dynamics, or we might find ourselves faced with evidence that our solar system serves as a relay station in networks of communication spanning the galaxy. The transition hypothesis transforms our sun from a simple star into a cosmic post office, and the October visitors from random wanderers into couriers completing routes that began in star systems whose names we do not know. Does this transformation reflect a true discovery, or merely the human need to find meaning in chaos? It remains the central mystery of our current cosmic moment. Part 13. The Harvest Scenario. Fields of fuel and solar fire as a cosmic gas station. The sun burns with the accumulated power of 4.5 billion years of nuclear fusion, converting 4 million tons of matter into energy every second in a process fundamental to our existence, one whose raw power we rarely contemplate. But what if our star represents more than just the anchor of our solar system? What if it serves as a cosmic gas station, a source of exotic fuel and energy that civilizations harvest on a schedule, measured in millennia, not in human lifetimes, an automated harvesting operation? Imagine Atlas and its squadron as components of an automated harvesting operation, arriving at our sun not by chance, but according to protocols established long before human civilization. Emerging from the African savannas, the smaller object plays the role of a surveyor and coordinator, measuring stellar output, plasma characteristics and conditions to optimize collection efficiency. 10 larger devices deploy a tenfold collection system, disguised as natural cometary activity, siphoning energy and material from the star's outer atmosphere. We are using technology that operates at the intersection of engineering and physics, a form of industrial camouflage. The harvesting scenario requires us to reimagine the spectacular sights of comets that we observe as camouflaged industrial processes. The beautiful tale of sunrise, stretching across many degrees of the sky, may conceal magnetic funnels designed to channel solar wind particles into hidden processing systems within what appears to be a coma. The anti-solar deflection of the ion tail, which we interpret as a passive response to charged particle pressure, could in fact represent controlled exhaust plumes from solar farming engines operating on a scale larger than any human industrial enterprise. The collection systems of this hypothetical magnetic field would need to operate with extraordinary subtlety to avoid detection by our increasingly sophisticated instruments. But advanced civilizations may have long ago mastered the art of working with natural forces rather than against them, creating technologies that enhance and direct natural processes, instead of replacing them with obvious artificial alternatives. What we interpret as normal cometary behavior could, in fact, represent the optimization of natural ion acceleration mechanisms for the purpose of resource extraction. Microscopic wormhole physics, the physics of these harvesting operations, extend into realms where current human understanding becomes tenuous. Consider the possibility of networks of microscopic wormholes, temporarily stabilized by the extreme gravitational and magnetic field conditions found near a star's surface. These microscopic spacetime conduits could provide instantaneous transport for harvested materials across interstellar space, eliminating the need for conventional propulsion systems to transport the harvested resources back to distant consuming civilizations. The extremely strong fields necessary to maintain such wormhole networks would exist naturally, only in environments like a star's corona, where the magnetic field strength reaches thousands of times that of Earth's surface. The magnetic fields and gravity wells reach limits where general relativistic effects become significant. Our sun's October visitors might be positioning themselves to exploit these unique physical conditions for a short period, when the field geometries are favorably aligned for their applications. Exotic physics, harvesting cycles, and optimization. Rhythmic pumping operations might follow cycles related to the sun's rotation, and magnetic variations that create rhythms of light and dark, which our instruments would record as natural brightness fluctuations. The sun's 27-day rotation cycle establishes natural rhythms in the magnetic field. Plasma direction and density that sophisticated harvesting systems could exploit for maximum efficiency. October of 2015 may have been an optimal harvesting window, determined by long-term cycles in solar activity and magnetic field configurations. The isotopic composition of the solar wind provides another potential target for advanced mining operations. Our sun produces helium-3 through its fusion processes, creating a light isotope that human fusion researchers consider an ideal fuel for advanced reactor designs. The natural solar wind carries this isotope throughout the solar system in concentrations too low for humans to harvest, but sufficiently advanced separation and concentration technology could extract useful quantities during close stellar approaches. Exotic matter and advanced manufacturing. The resource extraction motive might extend beyond the mere harvesting of fuel to include exotic forms of matter and energy, which exist only in stellar environments. The extreme temperatures and pressures within stellar chromospheres might allow for the production of exotic states of matter. Quark gluon plasma. Magnetic monopoles. or other theoretical particles that could serve as energy sources, or manufacturing materials for civilizations operating on a galactic scale. Historical parallels with human resource extraction, offering templates for understanding how star harvesting might operate. Our ancestors followed seasonal migration patterns to exploit temporary concentrations of game animals, edible plants, and raw materials. Modern industrial civilization established a permanent infrastructure near coal deposits, oil fields, and mineral mines to determine the locations of cities and transportation networks. Star harvesting represents a logical extension of this pattern to cosmic scales and energy sources. Sound and signal design. The sonic implications of such activities challenge the human imagination in the vacuum of space. No sound waves would propagate from these hypothetical harvesting systems, but electromagnetic signals could create distinctive patterns, recognizable to civilizations that know how to decipher them. A slow pulse in radio frequencies, a distant crackle as magnetic field, lines reconnect and release stored energy, all translated into electromagnetic rather than acoustic phenomena. Positional control requirements. The requirement for station keeping for any real harvesting operation would demand constant attitude control and position maintenance against the complex gravitational and magnetic forces at play in the stellar environment. These requirements would produce measurable signatures in the orbits of objects and their rotational states, which our instruments could potentially detect, if present. The absence of these signs in our current observations suggests that active harvesting scenarios are unlikely, but we must acknowledge the limits of our detection capabilities when faced with technologies that could be millennia ahead of our own understanding. Systems that maintain position and orientation by manipulating local magnetic fields could produce signatures so subtle that they remain below our current measurement thresholds. What might appear as the natural behavior of a star could in fact represent the execution of precise and complex industrial processes, ethical implications, and ownership. The ethical implications of stellar resource harvesting raise profound questions about ownership and territorial claims on a cosmic scale. If advanced civilizations regularly harvest energy and materials from stars across the galaxy, would our sun be a common asset, or does our presence in orbit around it establish some form of territorial claim? Would harvesting operations necessarily view emerging civilizations like humanity as owners, competitors, or irrelevant biological phenomena? Distinguishing between the natural and the artificial, interpreting the actual behavior of a comet versus imagined signs of harvesting becomes critically important for evaluating these scenarios. A natural ion tail points away from the sun due to radiation pressure and charged particle interactions, following known physical laws. Any actual harvesting activity would need to operate within these limits, or create detectable violations of the expected tail geometry and plasma behavior. Our current observations show the ion tail's behavior is consistent with theoretical predictions for natural cometary interactions with the solar wind. There are no anomalous accelerations, no violations of the expected tail orientation, and no evidence of controlled magnetic field generation beyond what natural plasma physics produces. The spectral signatures we detect correspond to known molecular species undergoing familiar chemical processes under the influence of solar heating. If harvesting operations were active in our solar system, we would expect to detect non-Keplerian orbital signatures, as harvesting systems maintain optimal positions relative to changing solar conditions. The absence of such signatures in our tracking data for both Comet Atlas and Comet Swan suggests that any forces governing their motion operate through gravity rather than artificial mechanisms. Psychologically, however, the harvesting scenario remains compelling. This is precisely because it transforms random cosmic encounters into elements of a vast industrial enterprise spanning both space and time. It suggests that our sun serves purposes far beyond merely powering life on Earth, that our star system participates in economic networks, operating on a scale that we can hardly comprehend. The 10-2000-215 convergence becomes a moment of cosmic commerce, instead of just gravitational mechanics, with both visitors playing specialized roles in the extraction of resources. Scheduled operations established long ago, before human civilization began to question the lights in the sky. If the sun is a station in some galactic resource network, how many routes regularly stop here and what do they carry into the cosmic night web? The answer may be written in the fire and plasma of the star's corona, readable only by an intelligence sophisticated enough to distinguish between the natural and what is harvested, purposefully in the dance of matter and energy that surrounds every star. Part 14. The conflict of rescue, retrieval, or purge. A theater within a theater, hidden behind the blinding light of our sun, where human telescopes cannot penetrate and only imagination can write the play. 2015 could witness the final act of a conflict, a cosmic one that has been simmering since the two visitors first appeared in our skies. 3 scenarios unfold in the realm of pure speculation, each one casting our mysterious visitors in roles, transforming them from passive wanderers into active participants in a larger struggle for control of information or cosmic security. The rescue scenario. The rescue scenario plays out as a tale of technological salvation, with Swanride arriving not as a separate visitor, but as an emergency response to a distress signal from Borealis. In this interpretation, the interstellar wanderer represents not a healthy probe, but a damaged scout ship, its unusual chemical signatures reflecting system failures, rather than exotic composition. The nickel emissions, unaccompanied by iron, could indicate hull breaches or component failures that are leaking materials, industrial into space. As the ship struggles to maintain basic functions, the dramatic arrival of Swanride from the solar convergence point takes on new meaning as an emergency deployment, its spectacular tail development concealing the rapid unfurling of rescue equipment and stabilization systems, the approach of the comet with an unrevealed orbit, placing it on an intercept course with Atlas during a critical phase of its solar encounter, when thermal stress and radiation exposure could complete the destruction of any remaining operational systems on the interstellar vessel. In distress, the staging of a rescue operation would require precise timing and coordination, easily mistaken for natural gravitational mechanics. Swanride would need to match the velocity and trajectory of Atlas, while deploying collection systems disguised as gas, outgassing from an active comet, which could involve the transfer of critical systems, evacuating data memory, or providing power and life support to the crew members who have survived years of interstellar travel only to face a systems failure during their final approach. In the recovery scenario, alternative interpretations suggest a scenario where Swanride acts as a collector rather than a rescue team, arriving to gather intelligence or retrieve equipment from a probe that has completed its mission. Atlas could represent a precision platform designed to gather specific information about our solar system, with Swanride acting as the mobile storage and transport system that would carry the collected data back to its point of origin. This recovery operation could involve the physical acquisition of the smaller vessel by the larger one, a process that might appear on our instruments as a collision or fragmentation, but instead of destruction, the apparent consumption would represent the successful retrieval of intelligence assets after mission completion. The unusual timing of both objects' solar approach provides optimal conditions for data transfer and physical recovery, while minimizing exposure to observation from Earth-based telescopes. Interstellar intelligence gathering might require precisely this sort of operation, this orchestration, with specialized reconnaissance probes designed to be disposable after each mission. The enormous energy cost of interstellar travel makes it economically unfeasible to return small vessels to their point of origin, but larger collection vehicles could gather them effectively, with many tasks completed while in orbit, allowing for an eventual return to base. The cleanup scenario. The cleanup scenario. Presenting the darkest interpretation of the October convergence with Swan Rye, arriving not to assist Bialis, but rather to erase the evidence of its passage through our solar system. In this framework, the interstellar visitor represents a beacon or communication platform that had exceeded its operational parameters, perhaps by transmitting information back to its controllers, or by revealing too much about its artificial nature through detectable signatures. Swan Rye becomes the cleanup team tasked with erasing the evidence of the technological visit before human intelligence could gather definitive proof of its artificial origin. The cleanup operation would include not only the destruction of Bialis, but also the dispersal of its remnants, in ways that would make forensic analysis impossible. Advanced disintegration technology could break down the probe into its constituent atoms, scattering them so thoroughly that no trace of their artificial arrangement remained. The timing of this hypothetical removal reflects a careful calculation of human observational capabilities and the upcoming obscuration from view as both objects sank into the sun's glare. By timing the cleanup operation to occur when Earth-based telescopes could not observe the process, the cleanup team ensured that no human instruments would record the actual destruction and the disposal of evidence disguising the technology. Each scenario requires us to reimagine the spectacular cometary displays that we observe as camouflaging operations, involving technologies operating at the intersection of physics and engineering principles that we do not yet understand. The brilliant tails and expanding comas could conceal energy weapons, matter disintegration systems, or exotic technologies, operating by manipulating solar energy and the observed magnetic field interactions. But these dramatic interpretations must confront the persistence of reality. Observational data shows no evidence of conflict, coordination, or artificial intervention. Both objects continue to follow trajectories determined by gravitational mechanics, displaying spectral signatures consistent with natural ice, sublimation, and dust emission. No anomalous accelerations suggest active maneuvering, and no electromagnetic signatures indicate artificial power systems or communication devices. Mars, the sole witness. Mars serves as our only potential witness to whatever might unfold during the critical encounter phases. With its orbiting spacecraft positioned to observe Atlas, during its flyby on October 3rd, these robotic observers carry instruments designed for planetary science rather than the detection of anomalous phenomena. But they might record evidence of any genuine interaction between our visitors that exceeds the bounds of natural behavior. Coordination by the European Space Agency of Mars-based observations represents our best hope for maintaining surveillance during the phases. When Earth-based telescopes lose sight of the visitors due to solar glare, the limitations of existing Mars orbiters mean that only the most significant deviations from expected natural behavior would be detectable at that distance, while the communication delay between Earth and Mars further complicates any real-time monitoring of a hypothetical conflict scenario. The signal travel time of 12 to 24 minutes means that any intervention or response from Earth would arrive far too late to affect events unfolding over minutes or hours, leaving us as passive observers of whatever transpires in the space between Mars and our Sun. The psychological appeal of conflict scenarios reflects the human tendency to interpret ambiguous events through familiar narrative structures involving struggle, resolution, and the triumph of one force over another. These dramatic frameworks provide emotional satisfaction by transforming cosmic coincidence into purposeful action, even if that purpose involves destruction rather than creation. An open ending awaits behind the sunlight. When the light returns and our telescopes regain the ability to track both visitors, we will count the same number of objects that disappeared behind our sun. Their orbits and behavior will match the predictions, based on natural cometary models. 2. We will face evidence that the universe contains conflicts and resolutions that unfold on a scale far beyond human experience and challenge our understanding of the intelligence that can be achieved when it operates beyond the reach of human observation. Part 15. The October Silence. The instruments fell silent, one by one, as both visitors sank into the intense glare of the sun, the observation instruments flickering and then going dark. The coronagraphs were saturated with light, the greatest performance in our cosmic neighborhood, disappearing behind a curtain of hydrogen fire, leaving us with only memories, speculation, and the patient ticking of atomic clocks, counting down to the day of revelation, a global wait. In government facilities and university observatories around the world, astronomers held their breath. Social media platforms buzzed with amateur theories and artistic interpretations. The absence of data became fertile ground for every possibility. The human imagination could conjure in this forced silence. Every scenario became equally plausible. Every interpretation carried the weight of potential, a spectrum of possibilities. Indeed, a range of outcomes stretched before us, like frames from an unfinished film. One object returns with altered colors or brightness, forever changed by its solar encounter. The other object appears dimmer than expected, or perhaps not at all, consumed by forces we can neither measure nor comprehend. The coronagraphs might reveal a delicate ring of debris where a single traveler once was, a testament to some cosmic transaction completed in privacy. Or perhaps nothing will have changed at all, except for our own yearning for meaning, our hunger for purpose in the dance of gravitational mechanics and the poetry of sublimating ice, the practical path that leads through patient observation and careful measurement. The observation window for Comet Swan peaks in late September and October, offering amateur astronomers the best opportunity to witness its spectacular tail sweeping across the evening sky. Comet Atlas will emerge from behind the sun in December if our models hold true, allowing professional instruments to continue their careful cataloging of its chemical signatures and orbital evolution. The current evidence points firmly to natural phenomena. Two remarkable comets converging in time speak to the mathematics of orbital mechanics, not the choreography of intelligence. The true scientific value lies not in confirming our wildest speculations, but in learning about the formation of other star systems, the chemistry of primordial materials, from the farthest reaches of our galaxy and the processes that shape objects, as they encounter the intense radiation of our sun in the void of our understanding. But in the gap between observation and interpretation, in the silence between data points, stories take root and grow. We are pattern-seeking creatures, living in a universe vast enough to hold both mundane physics and extraordinary possibilities. The October silence becomes a canvas, where we project our deepest questions about intelligence, purpose, and our place in the cosmic order. If an ancient machine kept an appointment with our sun, what would it find in our small corner of space? A young world containing a curious species just beginning to reach for the stars, already filling the electromagnetic spectrum with the chatter of its civilization. Perhaps it would find exactly what it was looking for, or perhaps it would discover something unexpected in the complex symphony of hope and human fear playing out against the backdrop of cosmic time. The finale awaits an answer when the December light returns, and our visitors emerge as instruments come back online, with whispered reports of position, velocity, and spectral signatures. We will have the answer to the question that has echoed through 14 chapters of wonder and speculation. A comet, a fortress, or a reply. Until then, we wait in the stillness of October, embraced by the sun's gravity. wondering what stories the darkness might be writing in languages we have not yet learned to read. The universe keeps its secrets,